Welcome to the Design Patterns course. In this course, we're going to cover the fundamental design patterns that all software engineers need to know. So, what is so special about using design patterns? What are they? First of all, design patterns are well-tested, reusable solutions. They are like a solution template for how to solve common software engineering problems. They are flexible and adaptable. You can use them in a variety of scenarios. And they save time because they have been used so many times that they have been optimized. They are not only well-tested and reusable solutions, they are also optimal solutions. So why would we use them? Well, you know when you use a design pattern that you're using something that has been utilized successfully in countless projects before. And they are like a common meta language for developers. If you and I both know what a singleton pattern is, then we already have a common understanding of everything about how it would be used or how it should be implemented. You can think of a pattern as a common vocabulary for architects. In other words, we are on the same page, and this is very powerful because it facilitates good communication. And that's true even if you code in different languages. If you and I work with different languages, you work with C# and I work, for example, with Java or Dart, we still will understand what a singleton pattern is. In other words, design patterns in general carry over to different programming languages. If you understand a pattern in a general manner, then you know that regardless of the language implementation, it will effectively offer the same useful, reusable solution. So in summary, design patterns are associated with good, well-organized software design. As developers, we are obviously prone to mistakes and sometimes inexperienced decisions. Think of design patterns as a bag of reusable experience from many generations of coders and software engineers that we get to use and learn from. Next, we're going to learn what are the design patterns covered in this course. In this course, we'll cover the 7 most crucial design patterns. Each pattern will be covered as follows. We will explain and explore the design pattern architecture. We will then implement this pattern with object-oriented Python. We will look into how this pattern helps good architecture. And in a practical manner, we're going to use all these patterns to architect and write a simulation of John Conway's famous game of life, which will run on your mobile device. Here are the patterns that we'll cover in this course. In the creational family of patterns, we're going to cover the singleton pattern, factory method pattern, and the builder pattern. The creational design patterns are design patterns that manage object creation mechanisms. They are designed to create objects in flexible and highly adaptable ways. These patterns offer the most reusable and flexible ways of creating object instances. Next, we're going to move into the structural family of design patterns. Specifically, we're going to look at the adapter pattern. Structural design patterns are design patterns that improve and simplify your designs by identifying the most efficient and reusable way of composing relationships among entities. This allows for the best and most efficient ways of creating complex hierarchies of objects. Lastly, we're going to move to behavioral family of patterns. Specifically, we're going to look at the strategy pattern, the observer pattern, and the state design pattern. Behavioral design patterns are design patterns that improve interaction and communication between objects. These patterns offer loosely coupled ways of allowing objects to talk to each other and exchange messages. Once you master these patterns, you will immediately see the world of coding differently. You will start seeing those patterns everywhere. Just remember these pattern families. We have creational, structural, and behavioral. They encompass a whole world of design patterns. Creational patterns deal with ways of creating objects or families of objects. Structural patterns deal with ways of managing complex object hierarchies. And behavioral design patterns deal with ways of identifying and improving object messaging. Next, we're going to learn as to why do you actually need software architecture. We'll see you in the next lecture. Great to see you again. Let's talk about why is it that we need software architecture. As you know, complex software systems are plagued with many issues. Timelines are stretched as requirements change. Multiple developers have a hard time coordinating their efforts. And often, there is code redundancy and poor documentation. This in turn creates issues with maintenance and overall flexibility for adding new features. In general, this means poorly designed systems that are hard to maintain and are not adaptable. One answer to all the cited problems is having a proper design and architecture. Think of a skyscraper being built, like the Empire State Building. There's always a high-level blueprint. This blueprint is used to show everybody involved, from architects to supply chain to construction workers to machinery scheduling, what is being worked on. And we want that kind of predictability and coherence in our software projects. In other words, we want to have a well-organized and cohesive construction site. So how do we achieve that? Let's look at the development cycle. You start with requirements. You gather and document all the requirements for UI, the UX, and general goals of the project. Once you have all that, what you do next is you do a design. You architect the system based on the requirements you've gathered. Finally, you implement. And this is where you code and test the solution to ensure that it follows the design and fulfills the requirements. Now, mind you, it doesn't have to be exactly this way, where first you gather all the requirements and then you do all the design and you do all the implementation. You could do it more in a manner where you get some requirements, you design it and you code it as a proof of concept. Then you go back to get more requirements, you add them to your design and you code it. So you start building it from a core system. No matter which way you do this, no matter how you follow this development cycle, you need to have a good design. In this course, we will concentrate on the design part, and we'll explore how design patterns facilitate and help achieve good software engineering. Let's look at all the different documents and artifacts that you will normally encounter in a project. You will have requirement documents, you will have design documents, you're going to have UI and UX documents, test suites and documentation for that. You're going to have deployment documents so that you can deploy your solution to a particular system. Once your system is running, you're going to have an audit and logs, which are artifacts and they're also documents, and you will also possibly have analytics. But of course, all of this revolves around the source code. That is the final outcome of all your requirements gathering and your architecting. But you'll also have architecture documents, and possibly you might have diagrams for your database as well. But what we want to talk here about is how design patterns facilitate good architecture documentation. To document and teach you those design patterns, we're going to use UML. So as you can see, projects will have many moving parts, but in the realm of software, the final product is always the source code, and good architecture is crucial. Design patterns help greatly in that aspect, and this is what we're going to explore in this course. Next, we're going to look at why are we going to use UML in this course. Welcome back. So why UML? Why are we going to use UML in this course? UML is a good tool to document something as well defined as design patterns. Design patterns are well understood, and UML communicates their structure very well. And that is because it is a highly visual representation. And while it is not easy to maintain UML diagrams when requirements change, for our illustrative purposes in this course, they are great. We'll only use two types of diagrams, class diagrams and sequence diagrams. There are many other types of UML diagrams, but they are not needed for this course. So let's talk about the two types of diagrams. Class diagrams are used to convey the structure of a design pattern. Here's an example. You see a director, a builder, a concrete builder, and a product. There is a relationship between them. You can see that a director aggregates one or more builders. You can see that a builder is an abstract class from which you could create specific, concrete builders. And you can see that what the builder does is it creates a product. Okay, that's great. So we kind of understand the structure. How does information flow? How does it actually work? Sequence diagrams are used to illustrate the interaction of the main objects and the classes. Here's an example of a sequence diagram. We have a client and we have two objects. We have a director and a concrete builder, just as you see in the class diagram. The flow goes as follows. A client creates a specific new concrete builder. it then creates a director initialized with that concrete builder. It then calls the director's construct method. And then behind the scenes, what the director does is it communicates with the concrete builder to build the different pieces of the product. So it can build part A, part B, part C, and then it delivers the product to the client. So what the director does, just like directors usually do, it coordinates possibly multiple tasks so that you get a well-organized object. And in fact, what the builder design pattern does, it is used to build complex hierarchies of objects. So because design patterns form their own blocks of interaction, we can study them independently, and UML is a great tool at that level of abstraction. In other words, we can concentrate on one design pattern, fully master it and understand it, and then move on to another. They're isolated. You can study them on their own. That's what makes this great. And it's basically following that divide and conquer approach. Next, we're going to have a look at the difference between organized and unorganized code. What you see here is a grid of simple rectangles. You can see that there's a very simple grid pattern. There is some color differences, but it's very simple in its organization. On the other hand, when you look at this looks more like a bunch of overlapping blobs with some larger, some smaller. It's not as well organized. If you think of these two as different ways of implementing code, you can imagine the one on the left as being nicely broken up, kind of like the divide and conquer approach, and well encapsulated. Whereas the one on the right has a lot of large pieces of code sitting in one place, and you can see a number of overlaps. In other words, the one on the left is more structured. The one on the right seems a little more chaotic. And then if you facilitate the communication between the two, you can see that it's easier to see who communicates with what on the left-hand side, whereas on the right-hand side, it's a little harder to discern a pattern. This is a visualization of what organized versus unorganized approach is. In this course, we'll strive to get you to the left side so that your architectures and your code are going to follow very nicely and well-defined patterns, as opposed to what you have with the more chaotic and unorganized approach on the right-hand side. Next, we're going to have an optional lecture, which is a UML refresher for those of you who want to refresh your knowledge of UML. Welcome back. In all the coding examples for this course, we will be using Visual Studio Code. So I will quickly describe and show you how to set up VS Code environment for Python. First, a few assumptions. You have Python interpreter already installed and running. I recommend the version 3.7 plus, so anything above that is good. You also have Visual Studio installed and running on your system. Next step will be to install a Visual Studio Python extension from the marketplace. And then after that, we'll go over a few Python environment commands which are run from the terminal. Let's go over them. Venv, or virtual environment, creates a virtual environment for our project. For example, in the terminal command line, you could write something like python-m venv, then you put the project path, the project in which you're working, but you also have to include the venv subdirectory because that's where the actual environment is going to be created. We will also be using pip, which is a package manager for Python libraries. Whenever we need a specific library to be imported, we will need to use that. For example, you could just say pip install and then you give the library name. We're going to go through these examples in this video so you will be able to see all of this in action. A few additional notes. We will mostly work with object-oriented paradigms. This means that we'll mostly work with object-oriented Python, and we'll try to keep it as purely object-oriented as possible. This means using the following: constructors and initializers, instances and classes, and we'll also use some inheritance. We will also touch upon thread safety when needed. So let's have a look at the actual process of making your Visual Studio Code ready for Python. To check the Python version, all I need to do is simply just run the Python command with the version. So this way you can check that your Python is installed and what version you have. You could also just do this. This is pretty much equivalent. The next thing that we're going to do is we're going to now start Visual Studio. Get rid of that. So Now we're going to install the Python extension. So you go into extensions, we're going to look for Python. We're going to grab this first one by Microsoft, IntelliSense. Just click on it and install. It will install a number of other sub extensions. Takes a little bit of time to install. All right, this is done. So now that we have the Python extension, what we're going to do is we're going to create a project folder. And I'm just going to do it right inside my little practice. I'm just going to create a folder. I'm going to call it Project 1. Get rid of this. And now what I'm going to do is I'm just going to open the folder, my C drive, in practice and project. You can do it anywhere and you can call it anything you want. So now that we have this, what I'm going to do is I'm just going to create a file and I'm just going to call it main.py. And as you can see, because of the extension, Visual Studio understands what we have here. So now what I'm going to do is I'm going to create a virtual environment. Let me just actually put some code in here first. So as you can see, we have simple, fully functional visual UI Python code. But as you can see here, that squiggly line under pygame tells us that it doesn't know, it cannot resolve it. In other words, it cannot import it. So we will need to do two things. First, what we're going to do is we're going to create a virtual environment. So the way we do that is we go into terminal and pay attention to where the terminal opens. It happens to open inside our project. So what I'm going to do right now, I'm going to create the virtual environment. This just shows me the current path, and I'm going to create the new environment inside the VNV folder. So this is it. So as you can see here, it has created a number of configuration files. Also, this is where the libraries are going to go. So we have our virtual environment. So what I'm going to do right now is I'm going to get rid of this and start a new terminal. And as you can see, at this point, because of this VNV in green that we have, the environment understands that this is now a virtual environment. So now what we're going to do is we're going to use pip to install this library above. So we're going to go pip install, and the library name is simply pygame. I'm just going to copy that, paste it here. So now I'm going to run this. And as you can see, we have our little pygame window and our environment is running fine. All right, so this is it. This is just me showing you how I set up my environment. But of course, if you're only using the interpreter and you're familiar with the way you're doing things, that's all good. As long as you're able to run the code, that's all that we really need to worry about. But because I will be showing you everything within the Visual Studio environment, it might be easier for you to just follow exactly what I'm doing. And therefore, I wanted to just make sure that you have an environment set up like I do. All right, thank you so much. And I'm going to see you in the next video. And as always, keep on coding. Welcome back. We will use UML to visualize two aspects of our learning. We're going to look at structural relationships between objects in our designs. This is where you see how all of the objects fit together. What are the relationships between them? And how are they built? We're also going to look at behavioral relationships between objects in our designs. This is where you see how the objects behave. How do they communicate with each other? The end goal is to understand what is being done and how it is being accomplished. To illustrate the structure of our design patterns, we will use a class diagram. A class diagram is used to construct and visualize object-oriented relationships. We use the diagram to capture the following information: class information such as attributes and operations, or basically methods. Here is a very simple abstract class. It's just your generic shape, but you can see that it has two attributes, color and location, and then it has three operations: get area, get color, and get location. You can also control the visibility. The plus sign here means that something is public. If we put a minus, it would, for example, be private, but we don't have to really worry about that in this course. The next thing that you have in a UML diagram is class relationships between the different classes in the diagram. The first type of relationship that we're looking at are generalizations. For example, We have an abstract class here, shape, and then we have 3 descendant classes, triangle, circle, and rectangle. All of these 3 classes, they inherit from shape. What we have here is inheritance, which is a generalization. The next type of relationship would be an association. Here's a UML diagram that shows a cylinder. A cylinder could be created from 2 circles and a rectangle. First of all, notice that cylinder is a generalization of shape, so we inherit from shape. And then also notice that we have elements, which is a list of shapes. And we stipulate that there are going to be 3 shapes in there. We also put a comment. So the idea here is that a cylinder is made up of 3 separate shapes. So this is an aggregation. In other words, the cylinder aggregates some elements that happen to be shapes. Now let's have a look at dependencies. Here's an example. It's exactly the same diagram, but here we have 2 things that I would like you to pay attention to. One is that we have put everything into a package. This means that all of these things belong together. And also notice that the calculator is not really associated with any class, but there is a dependency between shape and calculator. And what this shows you is that shape uses a calculator. So the dependency is much looser here, in a sense that a shape, in order to do something, needs a calculator, but the calculator is not part of shape. Alright, so let's kind of put all of this together and have a look at another UML diagram that represents a house. So notice first that we have an interface called iRoom. Notice then that we have an abstract class room. So what you have there is that room implements the interface iRoom. Then you have 3 generalizations of room. We have a bathroom, living room, and a bedroom. When you look at the house, you can see that the house has a lot of associations. You have an association where a house aggregates 3 bathrooms, there's 1 living room, and it has 5 bedrooms. The house also has 2 doors, 10 windows, and a garage. The house also has a pool. Now, I would like you to look at the difference between the 2 diamonds. There's a black diamond and a white diamond. When you have a black diamond, that means that whatever contains the other elements, so for example, house contains a bathroom. What a black diamond means is that you cannot have an instance of the bathroom unless you have a house. Or, to look at it in a different way, if I remove or destroy the house, the bathroom is going to go with it. This is the same for garage, window, door, because these are all inherent parts of a house. Notice though that a pool also belongs to a house, but it has a white diamond. And what that basically means is that we still consider a pool to be part of the house, but if the house goes away, the pool actually is able to stand on its own. It's not completely composited into the house. So that's just a simple example. And you can also see that the house, it depends on the electrical grid, but the electrical grid is not part of the house. It's a completely independent entity, but the house uses it, therefore it's a dependency. So this is a very quick refresher of class diagrams. Next, let's have a look at sequence diagrams. A sequence diagram is used to visualize object-oriented behavior. We use it to show message exchange over time, and we capture the following. We capture interaction information such as actors of operations, so basically what is part of the sequence, and method calls with data. For example, here's a very simple sequence diagram of how the cylinder would calculate an area. A user wants to get an area of the cylinder, so it calls the method getArea. Inside the cylinder, it creates a variable called areaSum and initializes that to 0. Then it goes into a for each loop. It goes through all the elements, which are shapes, inside the cylinder, and for each one of them, it calls the getArea for that particular shape, and when that gets returned, it adds that to the areaSum. And it does that for all 3. Once it goes through the loop, it puts the areaSum into the result and returns it to the user. This gives you an idea of not only what is happening, but also to some extent how it is being done. That was just a very quick UML refresher. Next, we're going to look at what makes great architecture. We'll see you in the next lecture. Welcome back. Let's do a quick refresher of the Python language with reference to object-oriented programming. And we're dealing here mostly with the version of Python, which is 3.5 or more. We'll discuss the following main concepts: classes and objects, encapsulation, inheritance, and within inheritance, we're going to talk about interface contracts, as well as abstract classes, And we'll also look at UML diagrams for Python object-oriented programming so that you have a good introduction to what to expect in terms of how code translates into UML diagrams and vice versa when you're looking at the rest of the course. All right, so let's talk about classes and objects. Classes are simple, or maybe more complex, recipes that are used to create two main things. We want to have a container for our data, so they provide a data container, which would mean variables or constants, and it also provides operations on data, and this would be functions or methods. We then can use the classes to create instances of objects which hold the specific data that we can operate on. And because we use classes to create instances, that's why we call them recipes. Here's an example of a very simple class in Python. We have a greeting class, we have a constructor which accepts a name. We can then initialize the name variable with the name that was passed in. And then we can define a method, for example, a say-hello method, which simply prints a personalized greeting message using the name attribute, which simply does this. So what you see here is a class. This is a recipe for greeting objects. So let's see how we would create a greeting object. And it's pretty straightforward. We simply specify that a greeting variable is equal to a greeting object constructed with the value John. And then once we have the particular instance, we can then call a method on it, which will specifically work on that particular instance. And since that instance was initialized with the value John, that will print hello, John. Here is what this would look like in a UML diagram. We have a class named greeting. It has a name variable, which is shown here as being private. In Python, you don't really have that kind of privacy like you do in other languages, but we want to show the intent of our design in the UML diagram. So if I want the variable to be treated as private, I'll show it with that little minus as being private. We then have an init method, which is basically a constructor. And notice that we're also showing self as being of the type greeting and name is a string. And then we have the say hello method. Now, this is a slightly awkward way of notating that. It's very, very language specific. We don't really want to have a super language specific UML. So I'm going to simplify it a little bit. And this is what we're normally going to be working with. We have a greeting class, it has a variable named name, and then we have a simple constructor, which is simply greeting that accepts a name. The reason why we don't show self here is because that's how the Python language works. You don't have to really add that into the UML diagram. Notice that when we actually create an object of the greeting type, we don't, for example, provide anything other than the name itself. So this is how you would do it in the actual code. You would basically say greeting is equal to greeting with John being initialized. Sometimes we will do a bit of a Java-like syntax and we're going to show it like this. And clearly this is not Python syntax per se, but what we want to draw your attention to is that we expect the greeting variable to hold the greeting type. That's why we put it on the left. Of course, this is not how we're going to show it in code, but this is how we're going to show you in the examples to draw your attention that we would like the greeting variable to be, what you see on the left, of the greeting type. Now, you might think this is a little strange to show that kind of notation, but as you will see a little bit later, you could have something that could, for example, follow an interface, which means that the actual type expected is different from the type being initialized, which is a little bit strange for Python, but it's very important when we deal with certain aspects of the design pattern. So I would like you to basically think of this as interchangeable. Obviously, the first one is the correct Python syntax, but the second one is just a little bit more explanatory, and it's going to be used more as an example rather than actual code. So this is basically how we would create a class in Python. You create the recipe by using the class syntax, create an init method, which is basically a constructor, and then you provide a number of methods that you want to operate maybe on some inner data. Perfect. Okay, so let's look at the next topic. So what about encapsulation? What exactly is encapsulation? In general, a well-designed class already achieves encapsulation, in the sense that it gathers all the relevant data and functionality in one place. It helps us with controlling complexity as well. In other words, when you encapsulate behavior, you can actually put a lot of very complicated code behind a very easy to use method. That's one of the main aspects of what encapsulation is all about. So do have the following points in mind. Make sure that you create classes for all the objects you need in your code. And also create collections of related objects so that they can be treated as units. This means that you start with very simple objects and then you can put them together into more complex objects, kind of like the way a house is made of different rooms. If a room was an object, we would define it first, and then house would be an object that is made up of rooms, which are other objects or classes. So here's an example. Let's say we have a class author. We have a very simple constructor. Basically, the constructor takes a name and a birth year for the author. We initialize it, and then we have a method which is going to be getAuthorInfo, which simply returns a string that encapsulates or shows the information about this author. So in this case, we simply return a string that is going to specify the name of the author and what year they were born. So this is one class. We've just created a very small, a simple recipe for what an author is. Next, we're going to create a class called book. Now, the book itself is a more complex class. It has a variable title, it has a publication year, but it also aggregates or contains within itself the author object. So in other words, a book is a class that aggregates or contains another class. And this is how you can build hierarchies of more complex classes or objects with relatively simple ones. So let's have a look at our book. So the book is going to initialize the title, it's going to initialize the publication year, and it's going to initialize the author. Next, we'll have a simple method, which is going to be getBookInfo. All of that does is it returns a string that basically aggregates all this information, such as title, which was by a particular author, and you get the author info from the author object, and you specify that it was published in a particular year. And this is how you would create an author object. And this is how you would create a book object, which aggregates the author object. So this is pretty straightforward, and this is how you would use it. You could, for example, say, let's print the book info. So what you have here is a slightly more complex hierarchy of objects. Now let's have a look at the UML for that. So the UML is pretty straightforward. We have a book which aggregates a single author. So what you have here is a hierarchy. A book can contain an author, and an author is a smaller encapsulation, and then book is a larger encapsulation that encapsulates another object. All right, so now let's have a look at inheritance. Very important object-oriented programming idea. Inheritance allows us to generalize. We can think of it as a tree which grows more complex as we keep on extending its branches. So it's almost like you start building more and more by dividing your hierarchy more and more. Basically, the idea is that we start with some property or behavior that is present in different instances or types of entities, and we then create new and more specialized versions of the parent by inheriting either data and or behavior in the children. You will see what that means in just a second. So let's say that we create a simple animal base class. So what this is basically just a generalized idea, recipe, that creates an animal that has a name, and the animal can speak, it can say, it can basically vocalize something. And all that this class does is basically says, let's initialize the name, and then let's write in the speak method where it prints basically that the name makes such a sound. So this is very, very specific. So let's assume that all animals make sounds, and let's assume that all animals have names. So rather than creating now a dog object that will have its own name and it will have its own speak method, we can actually inherit some of that already from the animal class. So let's have a look. So we can now create a dog class. So notice that dog inherits everything from animal. And then we are going to override. So we're going to change the inherited speak method. We're going to make it more specific to the dog, and we'll say, for example, that the dog barks. But notice that we did not have to reinvent the name. The name has been inherited already from the animal class. And notice another interesting thing. We do not have in the dog class, we don't actually have a constructor. Well, we do, but that constructor is inherited from animal. In other words, the same way you create an animal object, you will do exactly the same thing with dog. Now let's look at a different animal, cat. Again, simple idea. We just override the specific behavior of a cat, but a cat still inherits everything from animal. So now let's have a look at the objects of the derived classes. So we can say dog is equal to the dog class with Buddy, and then cat could be Whiskers. And then when we call the speak method on the dog, it will say that Buddy barks. But if we say for the cat, it will say Whiskers meows. This is very important to understand that what inheritance allows you to do is twofold. It allows you to inherit behavior and certain data from the parent class, but more importantly, it is still considered in the same category. So a dog is still an animal. A cat is still an animal. In other words, if the animal class, which is the parent class, has a method speak, we expect for both the dog and the cat, or any descendant of the animal class, to also have the speak method. And that's very important. You're not only inheriting, some methods and some data, you're actually inheriting an expectation of behavior. So let's have a look at what it looks like in UML. And in UML, it looks pretty straightforward. We have our animal class. The animal class has a name. It also defines a constructor, and it has a speak method. Now, our dog class, we're notating here that a dog has a dog constructor, but that actually constructor is inherited from animal. And then we override the speak method, and we do exactly the same thing for the cat. So this is pretty nice because what this shows us is that a dog is an animal. A cat is an animal. So whatever the animal class does in terms of behavior, you can expect that from both dog and a cat. So how does this extend to the idea of an interface? Well, that's actually very powerful. The concepts of an interface contract and an abstract class are crucial in software engineering. We'll be using them heavily in our design patterns, so I would like to make sure that you have both of these concepts well covered in Python. So, we will devote a whole lecture to those topics. I'll see you in the next video, and as always, keep on coding. Welcome back. In this lecture, we'll go over interfaces and abstract classes. Let's talk about contracts. A contract is like a promise that you will provide some specific behavior. In classes, this means that you promise to provide some functionality. As you've seen before with the animal, if I know that a cat is an animal, then I know that it can speak because all animals can speak. So in other words, I expect the cat class to fulfill the promise of the animal contract. One way to create a pure contract is through a concept of an interface. In Python, we do not really have strict interface syntax. What we can do is we can use an abstract class with no implementation to the methods. So let's have a look at that. So these are the imports that you would need for abstract classes. You would have to import ABC and you would have to import abstract method. So here is an interface contract, and children will have to implement all of the abstract methods. And in an interface method, what we do is we have no implementations, so we simply use pass instead of the function body. So for example, here is a simple class. It's called myInterface. Notice that it inherits from ABC. All abstract classes have to do that. And we define an abstract method called, let's say, myMethod. And notice that we put pass in it because we're not providing any behavior. And that is it. So now what we do is we're going to derive or create a class based on myInterface contract. And we know that since my class inherits from myInterface, it has to have the method myMethod. So what do? We define the myMethod, and then we put the specific implementation that we would like for that particular class implementation. Here is an example of another class that also inherits from myInterface, and it also has to fulfill the contract, and it has to define the abstract method myMethod, And here we do it with that print. And then basically all that we do is we can just create an object, like my object is equal to my class, and then you can just call the my method. And you can have the other object and you do the same thing, call my method. So this is pretty powerful because we can now use this idea of my interface as being a contract, which has, we know for sure, a method called my method. So I know that if I call that method on any object derived from my interface, I am guaranteed that I'm going to have an implementation of my method. Now, this is very, very important for design patterns. So let's have a look at the UML for this. So usually the way we will show it in the UML is we're going to just show it as an interface. Notice that there's no such thing as an interface in Python, but given what we have explained, you will understand the UML. And what you see on the right, the code on the right, is basically reflected in the UML diagram. We have a my interface, and then we have a my class and another class, which implement the methods of my interface. Okay, so how do we enforce contracts? We can use something known as type hinting in Python to enforce a contract. So this is our interface, just as before. We have our my interface. It's based on the ABC, which is abstract base class. And then we have one abstract method. We could have more, and this abstract method is not implemented. So here's what we can do. We can now create a class that is derived from my interface. So let's call it my class. And as you've seen before, we just implement the my method. That's great. But now let's say that we have another class, but it has nothing to do with my interface. And it has its own method called some method. Notice that we're going to create a method that expects specifically my interface contract to be passed as a parameter to this method. That's very important. And in this one, we'll call the my method. And why is this important? Because we are guaranteed that any descendant, any child of my interface is guaranteed to have an implementation of my method. So now we could pass into process my interface my class object and it will work perfectly. But if we pass the not implementing interface, we're going to get an error. So let's have a look. We create my object, which is my class. Wonderful. And we pass it into process my interface and that will work properly. But if I create an object of the type not implementing interface and I pass it into process my interface, we're going to get an error. All right, so now let's talk about abstract classes. Abstract classes are kind of in between normal classes and interfaces. So let's talk about partially implemented contracts, which is all about reuse. In many cases, you have actual functionality, not just a signature, but actual functionality behind the signature that you would like to have all child classes inherit. So as we've seen in case of like an interface, there is no actual functionality. These are just contract signatures. Every method is just a signature. The name and the parameters are just a signature of what is expected. But sometimes we already know that there should be some sort of a base implementation. So this is where you would use an abstract class. You can add specific implemented methods, and you can also add specific constants or variables that everybody is going to inherit, like you've seen with the case of the animal, where every single animal, like a cat or a dog or anything that has been descended from the animal class, automatically inherited the name. So let's have a look at this. Okay, so just as before, we have our ABC and abstract method import, and we will create an abstract class shape. We create a very simple constructor which accepts a color, and we simply specify that the color is going to be whatever the input color was. Great. But now we create an abstract method. We call it area. We put it a pass because different shapes will have different ways of calculating the area. We're also going to create a parameter method. Same thing. It's a pass because we don't know what the actual parameter calculation will be because that depends on the specific shape. And we'll have one more abstract method, which is going to be the description, and we will actually create an implementation of this method. So in other words, this particular method doesn't have to be implemented. The other ones have to be, but this one doesn't have to be. So let's have a look at the UML. This UML is a little more complex. So we'll use the kind of like deeper green to specify abstract classes. And as you see, we have our ABC, the abstract base class, which comes from the ABC import package. And our shape descends from that. Our shape has color. It has a constructor which accepts the color to initialize it, and then we have two abstract methods, area and parameter, that have to be implemented, and we have a description method which does not have to be implemented. And here you have an example of two derived classes. These are children. One is a rectangle, which defines its own width and height, and the other one is a circle, which defines a radius. Notice that neither of them has to override description because they've inherited it and they can actually use it as is. The only thing that they really need to do is they need to override the area and the parameter, because obviously for a rectangle, the area is going to be width times height, but for a circle, the area is going to be different. It's going to be pi radius squared. And obviously the parameter is also going to be different. Okay, great. So this is pretty straightforward. So as you can see, a shape is kind of like in between a contract interface and an implementation, kind of like a half-done implementation. And the whole idea here is of reuse. Why create a rectangle that defines its own description if you can already define the description in the parent class, and in most cases the children can use it? You basically are writing less code. So let's look at the actual code implementations for this. So the idea basically is that abstract classes can re-implement methods or keep the existing methods. So again, we're seeing this shape class here on the left, and then we have, for example, a rectangle class. And as you can see, the rectangle overrides the constructor. So this is important. Since rectangle inherits from shape the simple init color, the constructor color, notice that what it needs to do is in its own defined constructor, which accepts width and height and color, it has to delegate to the superclass, which is in this case the shape, to make sure that that constructor is invoked with the color, because the shape class knows what to do with the color. Notice that our rectangle class doesn't know what to do with the color, so it just delegates that. And this is the idea of reuse. And then the area and the perimeter methods are properly defined. This is just an example of how you would use it. Rectangle is equal to rectangle 405 red, and then we have the rest of the code. So this is a very important object-oriented paradigm, the idea of inheritance using abstract classes. All right, so this is a very quick refresher. Now we're going to have a look at very quick code examples, and we'll do that in the next video. All right, welcome back. Let's look at some examples of code that are going to solidify the two refresher lectures that we did about object-oriented programming with Python. So let's look at this first simple class. This is very much a classic example. We have a simple class called greeting. We have a constructor which accepts a name. The name itself is a public variable. Then we have an instance method, say hello, which basically prints the name to the console. Then the way we create an instance of our class is, as the example shows, we say greeting is equal to the greeting class initialized with the string John. That creates a specific instance in memory of the greeting class recipe as an object. And then, of course, we can manipulate the object, and the way that we do it here is we call the say hello method, and when the say hello method is called, it will print the name. So if I run it right now, it basically says hello John, exactly as what we would expect. And if I create another variable, for example, let's say greeting2, and I'm going to say, for example, Jane, and then if I print that, it's pretty obvious what we're going to get. When we say greeting2 and we run this, we're going to see hello John and hello Jane, of course. Now, what can we do with this class? This is a fully formed class. This is not an abstract class. One thing, though, that we can do, I'm just going to remove this for now. One of the things that we easily can do is we can actually use this class as some sort of a base class. So I can create another class called Better Greeting. Now, this Better Greeting class is going to inherit everything from greeting, so we're going to derive it from the greeting class. And then for now, we're just going to define the body as pass. What that means is that the Better Greeting class inherited everything from greeting, but it's not changing anything. So in other words, greeting and Better Greeting to some extent are equivalent. So for example, if I change this right now to Better Greeting, the output should be exactly the same as it was before. And as you see, we have hello John. Now, basically what is happening here is that the better greeting class has a constructor exactly just like greeting, and it has the say hello method. So one thing that I can do is I can override this say hello method. The way I would do it is just as follows. I'm basically using the name, and what I can do here is I'm going to print something else. I'm just going to say hello, and I'm going to just say better. That's it. This is actually a different implementation now, and if I run it now, you can see that we have hello better John. So what is happening is we have overridden the method that we have inherited from greeting. But that method from inside greeting, it is still sitting within the hierarchy that we have inherited. And the way we could do it is I can actually refer to it using super. Super refers to the base class. So if I go super and I invoke the inherited say hello method, what do you think is going to happen now? I'm going to give you a few seconds to think about it. What do you think we're going to see right now? Well, if I run this right now, we're actually seeing both. So as you see, when you overwrite something and you inherit it, it becomes part of you. When you overwrite it, what you're doing is you're basically kind of putting that one aside and defining almost like a new logic for that particular method. So this is pretty straightforward, pretty interesting, I would say, but very, very basic. All right, so now let's go to another example. All right, so here what we're looking at is an example of basically object aggregation. We have one class that aggregates another. So we have a class author, which is pretty straightforward. We have a constructor that initializes the inner name and birth year variables. And then we have a getAuthorInfo method that simply returns a string representing the instance data for the author. Pretty straightforward, simple class. Next, we have a book class. Now, the book class is just a little bit more complicated. Just like the author class, it basically has a constructor that initializes its inner data, and then we have a getBookInfo method which returns some information about the book. The thing of note here is that the book aggregates the author. In other words, the book contains a reference to the author instance. So this is to a great extent an aggregation. This showcases being able to build a more complex object out of simple objects. So this is a very, very simple example. Then what we do is we create an author object, we initialize it with George Orwell and 1903 as the birth year, and then we create a book object with a reference to the author object. So at the end, our book object not only contains its own data, but it also via reference contains the data for the author. And then of course we print it, and when we print it, we get the following. Basically, as we expected, we get 1984 by George Orwell, who was born in 1903 and it was published in 1949. And if you look at the get book info, you can see that the return basically gets the inner value of the title for the book, but then it goes into the author instance and then asks the author instance to get the author info. So we're following the API of the inner object so that it tells us something about itself. And this is basically what this example is all about. So let's go to the next code example. All right, let's have a look at another example. Here we're looking at an abstract class, a class animal, which as you can see is derived from ABC, which is the abstract base class. This is how you make abstract classes in Python. And we create two abstract methods. One is a sound method, and the other one is a description method. Now, what is interesting here is that this is almost like what you would consider an interface to be. The only difference is that our abstract method description actually has an implementation. So let's have a look at this. This is like a little bit strange maybe, but it's pretty interesting. Okay, so now that we have defined an animal base class, we're going to derive some classes from it. So the first thing that we're going to do is we're going to create a class dog, and you can see that it extends animal. And then what we're going to do, because we have to, we're going to implement the sound method, and we're simply going to say in it that we return the woof, so like a bark. Now, notice that because the description is an abstract method, we have to override it, but it doesn't mean that we have to implement a new one. So this is a bit of a trick. So what we're doing here is that in the dog description method, all we're doing is we're simply delegating back to the description implementation in animal class. This is why you see super.description. And we do the same thing for cats. So when you have cat, which is derived from animal, the sound is going to be meow, and the description is exactly the same as for the dog. So if we run this right now, you will see that the dog says woof and a cat says meow. So let's look at the description method. So if you go back up to the animal description method, you can see that what it does is it prints. First we have a self and then class and then dot name. That double underscore name, double underscore is actually a private class name. So for example, animal has a class name of animal, dog has a class name of dog, and cat has a class name of cat. This is why when we print it, you can see that it says dog says, for example, woof. And that is like an automatic variable that you get whenever you create a class. So what is interesting here is that the animal description method has proper access to the child class's sound implementation. So basically what happens is that, for example, when you take the dog instance and you call the description class on it, what it will do is it will call the super description, but the super description is actually still within, for example, the dog class. So when it says self, it will work on the current child class's instance, and that's why self.sound returns woof for a dog because of the fact that we have an implementation there. Now, one interesting variation that we can do is, why do we have to make it abstract? Well, we don't have to. If I remove this abstract method from here, what I can do is I can actually completely then remove the overrides. And if I do that, let's see now what this is going to run as. And as you can see, it does exactly the same thing. The main difference basically being that if you create an abstract method, you have to implement it. If it's not abstract, you don't have to implement it. But let's see if we can override it. What I'm going to do right now is in the dog class, I'm going to override the description method. So what I'm going to do is I'm going to create my own description. Instead of class name, I'm just going to basically say, my little dog says. So if we run this again, you can see that I can actually override the method that I have gotten before, but because the description method is part of the animal contract, anything that expects, for example, an animal will work properly. Okay, so this is it for this particular example. Next, we're going to have a look at an encapsulation example. Welcome back. Now, let's have a look at a slightly different example of using classes in Python. This is not an example that we have seen in lectures, but it does deal with something we have discussed, which is basically encapsulation. What you see here is a bank account class. This is a normal, non-abstract class. We have two instance variables in there, which is an account number and a balance. We initialize them in the init method, which is our constructor. And then we have two methods that deal with the balance variable, which is getBalance and setBalance. We'll get back to that in a second. And we also have two complementary methods for deposit, which is putting money in, and withdraw, which is removing money. So let's quickly look first at the two class variables. So what we have is we have an account number and we have a balance. Notice that we have a protected attribute, which is accomplished when you put an underscore before the name. And we also have a private attribute, which is achieved with a double underscore, which is basically name mangling in Python. Now, the private aspect that we achieve here is actually very good. You will not be able to access that variable directly through, for example, the account instance. You have to use getBalance and setBalance. Now, let's have a look specifically at the writing method, which is setBalance. What is important here is that we can put a precondition. For example, if the input balance is not greater than or equal to 0, then we consider that to be invalid. In other words, it doesn't make sense to set a balance of an account, in this case, to be negative. And notice also that we have a similar thing with the deposit. It's a modification function that basically changes the amount of money in your account. It does the same thing. It works with the balance variable. And we basically check if amount is greater than 0, then we change the balance. But if the amount is 0 or less, then we basically consider that to be an invalid deposit. The reason why this is important, especially in encapsulation, is because what we're doing is we're setting certain rules as to what is considered valid or invalid when it comes to the operations in our account. So, for example, the fact that we can set the balance not to any value that we wanted, but specifically only to values that are greater than or equal to 0, it's a way of controlling outside changes. So this is very important for encapsulation. And in general, when you're creating a class, you want to make sure that you have some sort of control over how the data is, for example, set, especially how the data is written. What you see here, if balance is greater than 0 or if amount is greater than 0, these are preconditions. Similarly, we have a withdrawal, which is like if you want to withdraw an amount that is greater than the amount you actually have in your account, you will not be able to withdraw it either. You need those kind of checks. You need those kind of verifications to be done by the class itself rather than having it external to the class, because what that means then is that the actual logic of how we work with an account is encapsulated within the account or within the bank account class. That's very important. So testing this code is very simple. We create a bank account with an account number and balance of 1,000. We can then print the account number. Notice that we can actually access the protected attribute. It is not really recommended. Usually, any kind of attributes inside a class, it's probably best to have some sort of a setter and getter so that you can control the precondition, which is checking when something is being changed, and also a postcondition to make sure that the changes are valid. So next we see the accessing and modifying the private attribute through a getter. So we can, for example, find out what the initial balance is. We then set the balance to 500 and then we have the updated balance. And finally, we have using public methods that internally use the private attribute. In this case, it would be deposit. We can deposit $100, then we can see what the balance was after deposit. We then withdraw 50 and we can see that the value is correct after that. And if I run this right now, you can see that it works perfect. So this is again just a very simple example of encapsulation that specifically works with being able to control how data is modified externally to the class. So this is a very important aspect of encapsulation. So this is just a quick kind of refresh for you in terms of how encapsulation works or should work. And next, we're going to look at how interface contracts work. And as stated before, understanding interface contracts is very important, especially for design patterns, because we're talking about software engineering patterns where contracts and a promise of what a class will or will not do is very important. All right, so let's have a look at what an interface contract is in code. So we start with something pretty fundamentally similar to what we have done before. We create a class myInterface, which extends from ABC, an abstract base class, and we create a method. We could create more than one, but here this is just one method. And the method is an abstract method, which means that it doesn't have to be implemented. Specifically when the methods are not implemented, it becomes an interface contract. And the idea basically is that you cannot really create an object from that class. You can only derive another class that will implement all those methods. So you can't really, for example, take myInterface and create an object with myInterface. You can't, for example, say something like this. This will fail. So if I, for example, ran it right now, as you can see, this failed. And there's a reason for that. And the simple reason is that basically the point of creating an abstract class with all its methods being abstract is that it's not supposed to be used to create objects. It's supposed to create a contract for derivative classes. And why do we need contracts? Well, the idea behind contracts is that if I create an expectation that some sort of functionality will always be available if I go through a certain interface, then you can create very extensive pieces of software that are very flexible. I'll give you a very quick example. If I create an interface that specifies shape, and the shape has a method called area, If I want to create a piece of software right now that will add up, for example, all of the areas of different shapes, I can write that piece of software based on the shape interface, not on the specific instances, like whether it's a triangle or a square or, for example, a circle. I don't need to know what the specific classes are. All I need to know is that all of them are derived from shape, and because shape would have an abstract method called area, then I know that any shape will have that. That's a pretty straightforward idea. Okay, so let's have a look. So once we have created the interface, what do we do with it? Well, we extend that interface. So we're creating a derived class, a child class, and in that class, we have to implement whatever the abstract methods are in the interface. So in this example here, we have one method, and notice that my class has to implement my method. And then if we create another class, which also is derived from my interface, it also has to implement my method. That's the idea of a contract. By contract, you have to do it. What that allows me to then predict is that if I create, for example here, my object, which is my class, and I create another object, which is another class, I know that both of my object and another object, they have to have my method. And that's really the idea, that if I know what the parent class is and I know what the APIs are, then I can basically work with any kind of object as long as that object is derived from that interface. So if I, for example, run this code right now, you will see that the output, even though we're calling exactly the same method, my method, for each of the objects, each one of them is going to have a different implementation and therefore different output. And that's wonderful because from the perspective of the code, it doesn't know which one it's calling. It simply calls the interface contract method, which in our case happens to be my method. That's all it knows. Okay, so next we're going to look at a slightly more complex version of this code that kind of shows us exactly how we can now use the idea of an interface to ensure that we follow a contract. All right, so right now let's have a look at an interface contract being used in an actual method. So we have our interface contract just like before. My interface is derived from ABC. It has one abstract method, and then we create two classes, my class and another class, that both are derived from my interface. So we know for sure that they're going to have all the abstract methods implemented. And then we have another class, which is just, it has nothing to do with our interface. So we just call it not implementing interface. It just implements its own particular method. So then what we do is we create a test method. And this test method, which we called here process my interface, is smart enough to know everything about my interface contract. And in this case, it knows that my interface has a method called my method. So what basically happens here is that this interface, if you pass it an object that was created or instantiated from a class that was derived from my interface, then this method knows that it will definitely have a my_method function or method. It knows that. On the other hand, if I pass to it the wrong interface, it will also know and will throw an error. So let's have a look at that. I'm going to run it. And if I run it here, you can see something very interesting. When you look at this particular error here, it basically says that not implementing interface has no attribute my method. Well, exactly, it doesn't. So the important thing about this process my interface method is that it is aware of the my interface contract. And this will be important later on, especially when we are dealing with design patterns where we specifically engineer contracts via interfaces to have very specific API, which can then be properly used by a client. And the important thing here is that this piece of code here, my process interface, it doesn't know anything about my class or another class. It doesn't have to know. All it knows is that anything that is my interface derived, so my class or another class or any other class for that matter that is derived from my interface, will have a my method. So it can call the my method signature because it knows it will definitely be there. So this is quite important. We're going to see that used in our design patterns. Okay, so next we'll see an abstract class that is somewhere in between an interface and a fully implemented class. We're going to be talking about an abstract class with some built-in functionality. All right, so in this particular example, we're going to look at a combination of an abstract class used as a contract. So we have a class here which is shape. We're going to use that as a parent class for all of our shapes. And our shape class is not a pure contract because, first of all, it has an instance variable, which is color, and it also has a description method, which is fully implemented. So the actual contract part spans all three methods, but the two abstract methods is what we would like other shapes, for example, rectangles or triangles, etc., to implement so that we can then manipulate different shapes only knowing that they're shapes. We don't care what shapes they are. So in our case, we have an abstract method area and we have an abstract method parameter, and we have also a defined method description. Okay, so let's have a look now at how we would use the shape contract. So what we do is we have a rectangle class, and the rectangle class, it implements the shape abstract class. Now, what we need to do is, because this is a specific rectangle shape, we need to define some extra data for it. So in this case, we're defining extra data as being width and height. So we create a constructor which accepts width and height, but we also need to accept color because we have inherited color from the shape class. So in this case, how we initialize our instance data is we set width and height to be the input width and height, but the color itself is passed on to the super constructor, which is basically the shape constructor that we have inherited. And then we define the two abstract method implementations for area and perimeter, specific to rectangle. And as you can see, the actual algorithm is pretty straightforward. For area, we're just saying width times height, and for perimeter, we just basically add the width plus height and we multiply it by 2. If you look at the circle class is really no different. The specific data for circle class is radius. We initialize the radius to the input data. We also initialize color through our super or through the shape constructor. And then we define the area and we define the perimeter. Notice that the implementation of area specifically knows how to determine the area for a circle using radius, and also for the perimeter, the same idea. We have a formula that uses the radius. Okay, so what's the big deal about this? Well, look at this little interface contract method, which is process my color. Notice that process my color accepts shape, and all it does is it simply prints the description. That method doesn't have to know what shape is being passed, because it's guaranteed that no matter what the shape is, whether it's rectangle or triangle, that method will be there. So that code can accept any shape, even shape that we have not created yet. We could create a new shape in a month, which will be triangle, and the process my color method will not have to change. That's the beauty of it. We can keep on extending the set of children for the shape class, but we don't have to change at all process my color method. This is actually great and makes for very flexible and reusable code. And now, if we just look at how we would create the two shapes, we have a rectangle which specifically creates a rectangle with a 4, 5, and red, so width and height and red. And we are doing that because we know what a rectangle needs. The same thing for a circle. A circle is defined with a radius. But notice when I call the process my color method, it doesn't have to know if it's a circle or rectangle. So past the initialization step, we can write code using contracts that don't have to know anything about what kind of child classes are implemented or will be implemented in the future. So to some extent, process my color is a future-proof method. That's the point of creating contracts. And if I run this right now, you can see that right here at the very bottom, it says rectangle has the color red, circle has the color blue. The beauty is that process my color doesn't know if it's a rectangle or a circle. It doesn't matter. All right, this is great. So we are at the end of doing a refresher for object-oriented programming in Python. Next, we're going to go into actual design patterns. I'm going to see you in the next lecture. And as always, keep on coding. Welcome back. In this lecture, we're going to look at what makes a good architecture. What are the hallmarks of a good architecture? There are a number of principles. We have loose coupling, which is weak knowledge association between components. We have separation of concerns, which is breaking your architecture into tiers. We have something called law of the meter, LOD. And we have the very popular S.O.L.I.D principles of object-oriented programming. Let's have a look at all of that in a little bit more detail. So what is loose coupling? As we stated, it's weak knowledge association between components, but what does that mean? Imagine that you have a number of classes. These classes will communicate. Here is an example of the different intercommunication channels that these classes use. As you see, it's a lot. Here's a very similar diagram, but it shows the classes with a much cleaner route of communication. The one on the left is an example of tight coupling. The one on the right is an example of loose coupling. Changes to one component least affect the existence or performance of another component. So when you look at the diagram on the left and you look at the diagram on the right, you can definitely see that any changes to class B when it's loosely coupled affect less classes than it does when it's tight coupling. And of course, that means changes to testing, changes to documentation. So in general, loose coupling is one hallmark of good architecture. Next, let's look at separation of concerns, breaking your architecture into tiers. What does that mean? Well, that basically means that you structure your architecture around main tiers of functionality. You can have, for example, a presentation layer. It could be your web UI. It could be your mobile UI. You would also have a business layer. That is where you have a lot of communication happening, deciding what is it that the user, through the presentation layer, what is it that they want. And then you would have a resource access layer, which would be data access layer. So as you see, we have split our architecture into three separate tiers: the presentation, the business, and reading and writing the data. The separation of concerns is achieved using modularization, encapsulation, and arrangement in software layers. The next thing that we're looking at is the law of the meter, LOD. First, each unit should have only limited knowledge about other units. It should only know about units closely related to itself. Each unit should only talk to its friends. It should not talk to strangers. And that unit should only talk to their immediate friends. So let's have a look at three classes. We have A, B, and C. And let's say that A can talk to B and B can talk to C. We can basically say that B is a friend of A, but C is a stranger to A. So A can communicate with B, that makes sense, but A should not communicate with C. That's basically what law of the meter states. A given object should assume as little as possible about the structure or properties of anything else other than its closest friends. And this is also known as principle of least knowledge. This leads us into the S.O.L.I.D principles, very important principles in software engineering and architecture. And this is what we're going to cover in the next lecture. Let's have a look at the S.O.L.I.D principles of object-oriented programming. We have a number of them. We have the single responsibility principle, which basically states that there should never be more than one reason for a class to change. Each class should only have one central responsibility. Then we have the open-close principle. Software entities should be open for extension but closed for modification. Then we have the Liskov substitution principle, which states that functions that use pointers or references to base classes must be able to use objects of derived classes without knowing it. The interface segregation principle states that clients should not be forced to depend upon interfaces that they do not use. And finally, we have the dependency inversion principle, which says that you should depend on abstraction, not concretions. Let's have a look at this in detail. First, let's look at the single responsibility principle. There should never be more than one reason for a class to change. Each class should have only one central responsibility. For example, it should only deal with persistence, or it should only deal with pre- and post conditions, validation in other words, or it should only deal with notification, or only with logging, or only with formatting, or only with parsing, or only with error handling. The idea being that a class should not deal with any collection of these. It should specialize in one thing. Now, what about the open-close principle? That software entities should be open for extension but closed for modification. Let's have a look at an example. Let's say we have a simple calculator class, and this calculator class has 4 methods or 4 functionalities. It can add, it can subtract, it can multiply, and it can divide. But imagine that somebody comes to you right now and says, oh, but you know what? I would like to have a business calculator or a scientific calculator. What should you do? According to the open-close principle, you should not change the calculator class. You possibly already have code depending on it. What you should do is you should extend it. You should create new classes that extend the calculator class. So your loan calculator, which could maybe calculate some monthly payments or some future value of your mortgage, you just create a new loan calculator. Same thing with a scientific calculator. If you want to add sine, cosine, and tangent, don't put it into the original calculator class, extend it. What about the Liskov substitution principle? Functions that use pointers or references to base classes must be able to use objects of derived classes without knowing it. For example, if class A is a subtype of class B, then we should be able to replace B with A without interrupting the behavior of the program at all. Here's an example. If we create an abstract class shape, and then we create specific concrete classes like triangle, circle, and rectangle, any code that uses shape to get area doesn't have to know anything about the actual specific shape that it's using, whether it's a triangle or circle or rectangle. If I want to find out the area of something, all I need to do is ask for its area. I don't need to know specifically that it's any particular shape. That would be the Liskov substitution principle. And you can see that the idea is that if I have code that, for example, calculates all of the area of all the shapes on the screen, and let's say that I add a new shape, some sort of an oval or maybe a cylinder, my code that calculates the area shouldn't have to change at all. If it changes, that means there's something wrong with your architecture. It shouldn't change because it is still a shape. The next one is the interface segregation principle. Clients should not be forced to depend upon interfaces that they do not use. Declaring methods in an interface that the caller doesn't need pollutes the interface and leads to a bulky or fat interface. Let's have a look at an example. Let's say that I would like to create a logging functionality. So I create an interface called iLog. Notice that the interface has only one method, which is log. So now what I could do is I could simply just create a DB logger automatically, and I could create a file logger automatically. But then I need certain functionalities like open connection, close connection. I could add, for example, open connection to the iLog interface, but then the file logger, which would extend it, wouldn't need it. That's the problem. If I put the open connection and the close connection inside iLog, the file logger would be using a fat interface. It just doesn't need it. What we're doing is we're creating a generic iLog, and then we're creating sub interfaces, ID, blog, and iFileLog, which allows us to specifically create two classes, dblogger and FileLogger, that use exactly what they need to use. They don't have to use some extra methods or anything like that. That is what the interface segregation principle is all about. The last one that we have is the D in S.O.L.I.D, is the dependency inversion principle, which basically says depend upon abstractions, not concretions. Imagine that we have a book service that creates a book. So we have two classes. We have a book service class and we have a book class. The book has a number, and this number needs to be generated. But because book service is the one that creates it, it would need to generate the number. Now, how would you do that? The best way to do it is to have the book service use an interface, which is an abstraction, that has a pretty generic method called generateNumber. Then, whatever number needs to be generated, the book service doesn't need to know what it is. The book service simply wants to generate a number. So whether the actual number generator happens to be ISBN generator or an ISSN generator is irrelevant to the book service. That is the idea. The book service depends on the number generator. It does not depend on the concrete elements. We will see quite a bit of this in our design patterns. To summarize, we'll do the following 4 things in this course. We'll learn about the most fundamental design patterns in the industry. We'll study them in a proper architectural context. We will see how they cover the solid and good architecture principles, and we'll use them practically in a project. Thank you for watching and listening, and I'll see you in the next lecture. Welcome back. Let's talk about our first design pattern, the Singleton pattern. Singleton is a creational design pattern that ensures that a class has only one instance and provides an easy global access to that instance. The pattern does not stipulate what to do with a singleton. This is where you can be creative. The main tenets of this pattern are: you have to ensure that the class has only a single instance. You have to provide easy global access to this instance. You have to control how it is instantiated. And any critical region must be entered serially. What this last point means, if there is any kind of thread safety issues, then you must ensure that whatever clients are calling the singleton, they are calling it one at a time. You have to serialize that access. Let's have a look at what the singleton pattern actually does. So here you have an instance of a singleton, and you have a number of clients. All of these clients are going to access just a single instance. All you have to basically make sure at this point is that the class has only a single instance. In other words, if one client goes to create the singleton and another client in a different piece of code also tries to create the singleton, both of these instances have to be the same one. That's what defines a singleton. What does a singleton do? That's completely up to you. When you see those little red rectangles and squares, this is just a way of me showing you visually that the singleton itself doesn't stipulate what you do inside. It only stipulates how it is created. What you do inside is really up to you. So what can we do inside a singleton? Like, what is it actually good for? You can use it for a variety of functionalities where you want to control that there's only a single point of access. For example, loggers, or caching, or thread pools, or database connections, or configuration access. All of those access the same elements. So for example, when you're logging, no matter where in your code you're actually doing the logging, it should all be going to the same destination. So the best way of doing that would be to use a singleton. Here you have an example. We have 3 clients and they all go into the singleton. That little red rectangle just stands for a logger. So what this singleton does is it logs to a singular log file. So in other words, any one of these clients, when they call the class, they don't even have to be aware that it's just one instance. But what is happening here is that you're actually ensuring that because it is a singleton, they are all logging to the same log file, which is exactly what you want. Here's another example. Consider caching. It's a similar idea. You have a singleton and all of the clients are going to hit the singleton, checking whether there's something in the cache. That little red square stands for caching mechanism, but that caching mechanism is wrapped inside the singleton. So all that the singleton does here is it ensures that all of these clients just access a single instance. How about database connections? Same idea. We have our DB connectivity and we have our clients, and the clients are hitting the singleton, and that red rectangle would be some sort of a database connection manager. Okay, so who came up with this pattern? Well, this pattern is one of the famous Gang of 4 patterns, and its motivation is stated as follows. In other words, why would we want to have something like a singleton? It is important for some classes to have exactly one instance. Although there can be many printers in a system, there should only be one printer spooler. There should be only one file system and one window manager. Whenever you need to ensure that all the colors are going through the same instance, that's when you're going to be using a singleton. And this pattern, the singleton, is oftentimes used with some of the other Gang of 4 patterns. It's used with Abstract Factory. It's used with a builder, which we're going to see because we're going to cover this in this course. Also in Prototype, S.O.L.I.D, as well as State. So we're going to see the singleton being used a little bit more in the rest of the course. When do you use a singleton pattern? When you want to control access to a shared resource. When not to use. You should use the singleton pattern with restraint and do not let it degenerate into just global access for everything. Global access hides dependencies and might make it harder to read such code. So make sure that you have a good reason to use this pattern. The main question you should ask yourself as to whether you're going to use or not use the singleton pattern is, do you violate the SRP, the single responsibility principle? If yes, then you should reconsider using it. In other words, if your singleton is doing too many things, you're actually violating the single responsibility principle. So if you're going to create a singleton, make it just deal with logging or just with file caching, etc., not with logging and file caching at the same time. So what is the design consideration? When designing a singleton, consider lazy construction, which means that the class instance should only be created when it is first needed. In some cases, we might consider eager loading, if, for example, we need the singleton to be always ready and loaded fast. The main difference here is very much with memory. For example, if you're creating a game, if it's some sort of a shooting game, you want the sounds of the bullets to be happening every time a bullet is fired. At that point, you would eagerly load the sound so that it would be ready the moment the first bullet is fired. Lazy construction or lazy loading would be when you're not 100% sure if a particular instance is going to be used. So if you're not sure about that and you don't want to waste resources, then you can consider to load it only when it's actually accessed for the first time. Now, the other thing you have to consider is thread safety. You need to consider that specifically in languages that allow multi-threaded access, because you need to ensure that access is properly controlled and locked, so that the state of the singleton, if it has one, is always deterministic. Because Python does support multi-threaded programming, we will need to take special care when creating multi-threaded singletons. We will need to lock the critical section. That is something that we're going to look into when we look at the coding. All right, well, I hope that you found this informative and helpful, and I'll see you in the next lecture, and please do not hesitate to ask any questions you might have. I would love to answer your questions. See you in the next lecture. Welcome back. Let's have a look at a generic implementation of the singleton pattern first before we go into the specifics of coding it in Python. There are a few ways in which we could implement the singleton pattern in Python. So first, I would like for us to look at the generic architectural implementation, which we're going to use as a starting point. So I would like you to note a few things about this UML diagram. First of all, we have a private constructor. This prevents instantiation of the class by an external caller. Secondly, we have a private instance of the singleton class itself. Note that this instance is static. This means that it is defined at the class level and not at the object level. So there can only be a single instance of the singleton class globally. We obtain the instance by calling the static getInstance method, which does a very simple test. If the instance variable is null, we create a new singleton object and assign it to the instance variable. And since we're inside the class body, we can invoke the private constructor. If it is not null, we return the existing instance variable, which is always the same. Note also that this is an example of lazy instantiation. We only create the instance when we are asked for it through the getInstance method. So in essence, the singleton class creates its own instance. This is why you see the creates dependency. So this is a generic example of how you could achieve the singleton pattern. But how would we accomplish this in Python? Python is a very rich language, and there are multiple ways of implementing the singleton pattern, but there are some limitations. First of all, Python does not really have constructors, but it does have a creation and initialization routines for classes. It does not strictly have a static keyword for variables, but it does support class-level variables and methods which are, for all purposes, static. The singleton pattern can be implemented in a number of different ways in Python. Some possible methods include base class, decorator, or a metaclass. From those, the metaclass is the best suited for this purpose, since with it we can manipulate and control the task of the class creation itself. Before we look at the specific implementations of the singleton pattern, let's do a very quick review of some of general Python function overrides. So we have new, which is a static method that is responsible for creating and returning a new instance of a class. And it is the first step in the object instantiation process. It is typically overridden when you need to control the object creation process. That is definitely something that we'll need in a singleton. The other one that we're looking at is the init. This is an instance method that is responsible for initializing an object's attributes after it has been created by new. The init method does not return a value and it's called automatically after the object is created. This method is typically overridden to define custom attribute initialization for the class. And we also have the call method. This is also an instance method that allows a class's instances to be called as if they were functions. We'll see why that is relevant. So let's look at those in the context of Metaclass, which we're going to use to create the best version of the singleton. So new in this context, since a metaclass is a class that creates other classes, new in a metaclass is responsible for creating and returning a new class object. Init, this method is responsible for initializing the new class object created by the metaclass, such as setting class attributes or other class level properties. And call, in a metaclass, this method allows instances of the metaclass, which are class objects themselves, to be called as if they were functions. Now, this is executed when creating instances of the classes created by the metaclass. So by customizing this method, you can control how instances of those classes are created or returned. So we'll need to remember these definitions when we're actually looking at the singleton implementations. So this was just a quick overview or maybe a refresher. What we're going to do right now, we're going to build 3 different versions of the singleton, progressively from a good one to a better one to the best one. So what we're going to do is we're going to create a classic gang of 4 singleton in Python. This will give us the most simple and generic version. And in this one, we will need to control constructor access. And instantiation of our singleton will be done through a static method. Next, we're going to have a simple or maybe like a bit of a naive Python singleton. That will be our second version. And in this one, we're not going to control the constructor. So instantiation will be done through constructor. We will use the new method override to achieve this. And then the best version will be done using the metaclass. So we're going to have a metaclass singleton. And here we will override the call method. And we will also use the new and init methods, but we'll see that in later examples when we talk about eager instantiation. All right, so let's have a look right now at the actual implementations of these 3 versions of the singleton. Let's look first at the classic gang of 4 approach to singleton implementation in Python. Have a look at this particular UML. We have a static instance variable that holds the only instance of the class, and we initialize it to none. So initially, basically, it is not set. We then have a constructor that cannot be called. We show it here as private. I'll explain that in a bit, but the main idea is that we remove the ability for the caller to create more objects through a constructor. So this is the way in which we control instantiation. We then have a static getInstance method, which is how we will control the creation process. So let's have a look at the actual code itself. So notice that we have the class level variable to store the single class instance. The trick here is that we override the init method to control external initialization, and we simply throw an error if anybody uses a constructor. So basically, we remove the constructor at runtime. So this is not really a private constructor per se, but we do not allow its usage externally. We raise an error. Then we create a class level getInstance method, which allows us to fetch the single instance copy of the singleton. So basically, if the instance has not been initialized, then we initialize it to an instance of our classic singleton. Otherwise, we simply just return the instance back to the caller. How do we use this particular version of our singleton? We simply call the class level getInstance method to get the instance of our singleton. Also, please notice that this is an example of lazy instantiation. So what we get here is a legitimate singleton, but this is not necessarily preferred way of doing this in Python. Let's look now at a more of a Python kind of way of implementing our singleton. So this is a simple way in which we could create a singleton in Python, and it would be done as follows. So as you can see, this time we have a singleton where we do not control the constructor. Just as before, we have the instance static variable and we have a constructor. So let's see how it is that we actually control now the creation of this instance so that there's only one instance of the singleton globally. So let's have a look. As usual, we have the class level variable to store the single instance of our class. We set it to none. But this time what we do is we implement the singleton by overriding the new method, which gives us control over how objects are created. So what we do here is we check if the instance of the class has been created before, and if it has not been created, we create it. We then assign it to our class level instance variable, and then we simply return either the one that we have just created or one that has been previously created, but it is always the same instance. And this is how we would use it. So this way we're actually going through the constructor. And also notice that this is yet another example of lazy instantiation. So this implementation will work, but there is a syntactically and logically a much better and a more sophisticated way to implement a singleton in Python, and that is using Metaclass. And Metaclass will not only allow us to create a better version of the singleton, but it will also allow us to control both the lazy versus eager instantiation of the instance. So we'll do that in the next lecture. I'll see you in the next video, and as always, keep on coding. Welcome back. Using the metaclass is probably the best way to create a singleton in Python. A metaclass in Python is just a class that defines the behavior and rules for creating other classes. In other words, metaclasses are like the classes of classes or like factories of classes. By default, all Python classes implicitly inherit from the type built-in class, which is itself a metaclass. Metaclasses allow us to customize the class creation process and modify class attributes, methods, or other properties before the class is actually created. They provide a way to apply certain behaviors consistently across multiple classes. So let's have a look at one way of implementing the singleton using a metaclass. What you see here is a singleton meta class and a singleton class. What is interesting here is that the actual logic for what makes this a singleton is inside the metaclass. So just a quick description of what we see in the UML. The instances is a dictionary that stores, in our case, the single instance of the class for each subclass. We have only one subclass here, which is the singleton, so we will store basically the single instance of the singleton. Now, whenever we create instances of the singleton class, they will actually be handled by the call method override of the singleton meta class, ensuring that only one instance of the class exists. So to some extent, what you're seeing here is that the singleton class is actually created within the singleton meta class. So let's have a look at the actual source code. So we define our singleton meta class. The parent of this class is going to be type. Then we define a dictionary that stores the single instance of the class for each subclass of the singleton meta class. In our case, we have only created one subclass, which is the singleton. So this is our dictionary. Then we have the call override. And what happens is in the call, we basically check, hey, if we don't have our class inside the class instances dictionary, we create the instance of the class that is calling this, which would be the singleton class. And what we do then is we take the instance of that class and put it inside our dictionary. This ensures that we have only a single copy. And then we have a return. We simply return whatever we have there. And now our actual singleton class can do whatever it wants. So our class singleton depends on the singleton meta class. So the singleton here itself does not define the logic for the singleton. That is defined in the singleton meta class, which is actually pretty wonderful, because if you think about it, we could create one singleton meta class and then we could have many other subtypes that are also singletons, but we don't have to keep on redefining it. It's almost like a bit of an abstract class in that sense, in terms of behavior. And how would you use this? Just like any other class, you would simply say S1 is equal to singleton. We call our normal constructor, and that would be basically it. One thing to notice, of course, is that this is also lazy instantiation. Okay, So now let's have a look at how we would do eager loading. So let's look at what eager loading is good for in the context of a singleton, because every singleton so far that we've seen uses lazy instantiation. Okay, so let's first discuss why would eager loading be good. So first of all, eager loading allows for data preload and caching. It allows for connectivity pre-caching. It's important when access is frequent and needs to be fast. So we initialize a load the instance before we need it. That would be the idea of eager loading. You load it before anybody asks for it so that when they actually ask for it, it's already there. We don't have to create it. We don't have to build it. We don't have to get the memory for it. Everything has already been done. Now, Python does not support eager instantiation out of the box or, something in an elegant manner. But using Metaclass, we can achieve eager instantiation when the Metaclass is executed. So let's have a look at that. Okay, so let's look at eager Python implementation. So using the Metaclass, we can create an eager loading singleton. This is very similar to how it was before. We have a Metaclass and we have our singleton class, which is derived from the Metaclass. The difference here is that what we do is we override the init method before we deal with the call method. Now, the init method is called before. And what is important here is that the singleton metaclass is going to be loaded into memory before anything else is executed because it is a metaclass. So therefore, if we want to generate eager loading, all we need to do is override the init method and then in the init method, create the instance of the singleton. So let's have a look at what that would look like. So here is our class. We have the same dictionary as before, that has not changed. But now what we do is we override the init method. And in the init method, what we're doing is we do an eager loading of the class. And then once we have eager loaded it, then we override the call method. And in the call method, we simply return already loaded instance of the class. And here is our actual singleton class. You can do the definition in it because that's where you can, for example, create whatever initialization you would like to do for your singleton. Now, how does this actually work? Whenever you run your code, even before your code actually executes any lines of your source code, it will load all of the class definitions inside the memory. So when the singleton meta is loaded, it will load all the classes that depend on it in the init method. This is how you would actually call it, exactly the same as before. And this is eager loading, as you will see later on when we actually run the code. Here's a few things to keep in mind when implementing the singleton pattern in Python. As you've seen, in some cases, we're using getInstance versus a constructor. Now, using getInstance might sometimes be syntactically and architecturally a little bit better, because it allows for consistency of usage, it provides flexibility of easy modification of the initialization logic, it allows for ease of expanding the setup and initialization code, and it creates a better flow than a constructor since the name could be uniform across different class names and implementations. And that's quite important because if normally looking at a class, you don't know if it's a singleton. But the moment you see that you have a getInstance method, that might right away give you a hint that this is actually a singleton. All right, so next, we're going to look at how to deal with thread safety issues with our singleton implementation, and we'll look at how to use the singleton in some practical examples. All right, so I'm going to see you in the next lecture, and as always, keep on coding. Welcome back. One of the tricky things with writing a singleton implementation in Python is that we need to worry about thread safety. All of the previous singleton examples are not inherently thread safe. If multiple threads try to create or access our singleton object at the same time, it can lead to race conditions and other issues which could create subtle and hard to debug erroneous behavior. You do not always have to create a thread-safe singleton, but in some cases it is very important. So we will explore how to create a thread-safe version of our singleton. So let's talk quickly a little bit about thread safety as a refresher. So basically the idea is when you write your code and you have multiple threads in it, for example, thread T1 and T2, what happens is you might have in your code something known as critical section. Now, the main task when making something thread safe is to make sure that only a single thread at a time can access the critical section. What is a critical section? A critical section is the area of the code where allowing multiple threads to write data can create unpredictable behavior. Establishing the part of the code that is a critical section can be tricky, but usually involves areas of your code where data is changed. So how do we ensure that only a single thread at a time can access the code? In this example, what you have is you have T1 and T2 both enter the critical section where they can both execute the code that works on the data. And then they both could literally leave the critical section. The problem with that is that we simply don't know what the state of the data is going to be. Because depending on the timing of the running of the two or more threads, the outcome could be different. That's why this is called a race condition, because what you have is you have a number of threads racing to change something about the data. And because we don't control which thread goes there first, it becomes unpredictable and actually can create very strange results. Okay, so how do we ensure that only a single thread at a time can access the code? We use a lock mechanism. So here's a simple visualization of how thread safety operates in a Python environment. So again, we have code, we have our critical section, and then what we have is we have a lock. So the lock is basically used to protect our code from race condition. So we have two threads come in. Before any one of those threads can go into the critical section, they have to go through a lock. And then what happens is that one of them is going to acquire the lock. That one could be T1, for example, in our example. It will hold on to the lock, which means that it is the only one allowed inside the critical section. But what happens to T2? T2 is put into a special queue, which is a waiting queue. So basically, as long as T1 holds on to the lock, T2 is going to wait to enter the critical section. Let's assume, for example, that at some point another thread shows up, T3, and it also wants to execute the code in the critical section. But because it has to go through the lock, it will also be put inside the waiting queue. So now what happens is that eventually T1 is going to be done and it's going to go outside of the critical section and it's going to relinquish or give back the lock. So then what happens is the queuing mechanism is going to take T2 out of the queue and it's going to give it the lock and it's going to put it inside the critical section. So as long as we know how to create such a lock, we can protect the critical section from any kind of race condition issues. Okay, so let's have a look at an example of very simple thread-safe code, not a singleton per se, but just a thread-safe code. Let's say we are creating a class called counter. And this counter class is going to do a very simple thing. It's going to take a piece of its data and it's just going to add 1 to it. We initialize the count itself to 0. We also initialize lock to a lock class variable. And then what happens is we have a method called increment. This method will be our critical section. What we do now is before we change our count data, we acquire a lock. That's the part that you've seen where the two threads came in and only one of them is guaranteed to acquire the lock. We don't necessarily know whether it's going to be T1 or T2. The problem is not basically which thread gets access. The problem is just that only one gets access. That's the important thing. So if two threads are going to call this, only one of them is going to acquire the lock, and the one that acquires the lock will be able to then execute self.count and add 1 to it. That part is the critical section. Once it's done with it, it will then release the lock. When it does that, another thread that was waiting could go in. So this is simply an example of a thread-safe code in Python that protects a critical section. Our critical section here happens to be just one item of data, which is count. So now let's have a look at a thread-safe implementation of the singleton pattern. So we'll import threading, we'll have a thread-safe singleton, we'll have a class level variable, which stores the instance just like before. And also we will have a lock. Notice that what we're doing here is simply just creating a lock variable. We're not locking anything yet. Now we'll have a new method. This is our critical section, which is our constructor. And inside the critical section, we're going to acquire the lock. And once we have acquired the lock, we're then going to check if we have created an instance before. And if we haven't, then we create the instance and we return it. And that's basically it. You can at that point either release the lock or simply returning releases the lock. And how would you use the thread safe singleton? Pretty simple, just like everything else. In this case, we're just using the constructor. So what is really happening here? Notice that the lock variable is a class level lock that is used to ensure thread safety. The new method is used to create the single instance of the class in a thread safe way because it uses the with block to acquire the lock before creating the instance. And if the instance has already been created, the with block is skipped and the existing instance is simply returned. If the instance has not been created yet, the with block is executed and the instance is created. So this is pretty straightforward, simple example of a thread safe singleton. All right, this is it for this lecture. In the next one, we're going to look at some practical examples of how to use a singleton. Okay then, see you in the next lecture, and as always, keep on coding. Welcome back. Let's have a look at examples of how the singleton can be implemented in Python in code. Let's look at this first example, which is basically the classic singleton in the style of gang of 4. As you can see here, we're overriding the init method to control initialization. So for example, if I run the code as we have right now, as you see, I am actually invoking the constructor here. If I run this right now, you can see that we have an error. We have the runtime error, which is basically this error right here. So what we have done in this implementation, we are overriding the init method and we basically do not allow instantiation that way. So we're controlling external instantiation of this class by disallowing the constructor. So then what we do instead is we create a getInstance method, which is a class level method or a static method. And what we do there is through the instance variable, we control the actual class level instantiation. The underscore instance variable is a class level variable and it's going to store the single class instance. In the getInstance method, what we do is we simply check whether the instance has been initialized, and if not, we initialize it. We create a new instance of the class and we assign it to the instance. Otherwise, if it already has been created before, we simply return that particular instance. In other words, we always create the same instance, which is the definition of a singleton. Now, let's actually run this as is properly stipulated by the contract here. We can call the getInstance method, class level method, to get the actual instances. So as you can see here, we have S1 and S2. And if this is working correctly, then when we print S1 is S2, we should see true. So let's go back here. I'm just going to clear that and we're going to run this. So what you're seeing here is that the getInstance is called twice because that's where we have the print statement. So this is correct and it's true. And also it outputs the memory location of the object, and you can see that they're exactly the same as it should be. So this singleton implementation works pretty well on the surface, but now let's have a look at the other implementations. Here, we are looking at an example of a simple singleton implementation. We override the new method, which allows us to control how the objects are created. And the logic is exactly the same as we did in the gang of 4 getInstance method. We simply check if we have our instance variable set, and if not, we set it with a new instance. And if it is already set, then we just return that instance. So it's really not that much different. We are not overriding the new method to disallow the usage of the constructor. So the way that you would call this is pretty simple. You can use the singleton constructor. So if I run this right now, the printout should be true. So if I run it right now, it tells you that it's creating. So basically at each call of the singleton, it goes into the new method, which is obviously what is expected. But then the most important thing is when we print S1 is S2, it becomes true. Okay, great. So this is pretty simple. This is probably the simplest singleton implementation. But let's look at one more thing here before we get into the other implementations. Let's look at this override. All I'm doing here is I'm just overriding the init method to kind of like show you the specific order. I'm going to clear the output here. And I'm going to run this one more time. And now as you can see that new is called and then init is called and then new is called and then init is called. You can see it here in the printout. So what basically that tells you is that new creates an instance and then init initializes it. Okay, great. So this is just a quick, simple little thing about the Python language. But one thing that would be important, and this will become obvious why this is important when we go into the metaclass implementation. If I remove this code right now, right here. All we have right now is just the code for the class Singleton, nothing else. I'm going to clear this again. So now the question would be, if I run this code right now, is anything going to happen? You can pause this and think about it for a second, but I'm going to run it. And as you can see, nothing happens. Well, to a great extent, that makes sense. Nothing has happened. The only thing that has happened is that the class Singleton has been loaded into memory, but nothing has invoked it, which is why we don't see any output. We don't see any of the new or the init printouts being called. I just want you to remember that for when we go into the metaclass. Let's now have a look at some of the metaclass implementations. All right, so now let's have a look at how we could use a metaclass to create a singleton. So what we're doing here is we have two classes. We have our singleton meta, which is the base class for our singleton. And notice that what we do here is we use the instances to hold an instance of any of the single meta children. In our case, we only have one child, which is the singleton class. So inside the instances, the actual element, the only element that we're going to have in there is going to be a singleton entry. Instances is a dictionary or like a hash map where the key is the name of the class. In our case, it's singleton, and the value, if there is one, would be the instance. We override only one method inside the singleton meta, and that is the call function. So what happens here is that if the singleton constructor is invoked, the call method is going to be invoked. So let's run this and see what we're going to get. Looking at this, what you would expect is that we're going to run singleton for S1, we're going to run singleton for S2, and then we're going to print whether S1 is actually S2 because we want to have obviously a singleton. But notice that I put a print statement here, which is basically whenever the call function is invoked in our single meta, then this print is going to be printed. So what we expect here is that when I run this, we're going to see two of those. So let's run this right now. So we do see two of them, and we see that the singleton is working well, that it's true. This is great because what this allows us to do is it creates a separation between the definition of the singleton, which is inside the singleton meta, and the actual singleton functionality that we would like to have, which would be part of our singleton class. And this is where I've put a very simple little stub for some sort of a business logic, which is the definition that you see there. One last thing that I wanted to show you, I'm going to clear this, is if I remove this, right? So right now, we don't have any actual code running. And if I run this, nothing happens. This is what we expected. But in the next example that we're going to see how to do eager instantiation. All of these are lazy instantiations. The only time that you see that the call meta is being actually invoked is if we actually call the constructor, if we actually ask for it. So this singleton meta is definitely a lazy instantiation. So now let's have a look at an eager instantiation. How would we do that? All right, so let's have a look right now at two different eager singleton implementations. So you see we have two pieces of code right here. We have one where we override the init and we override the call in our meta definition. And then we have another one where instead of overriding the init, we override the new and the call. And in both cases, the actual singleton class after that basically just does the same thing. It just implements some sort of an init of its own to, for example, initialize its own attributes. So what I would like you to do first is observe the following very interesting things. So what I'm going to do is I'm going to go into the first eager implementation, this one right here. And what I'm going to do, as you can see, I have some print statements here. I have a print statement right here in the init method of the singleton meta. And I have an init right here in the singleton. So what I'm going to do right now is I'm going to remove this code, which is actually the code that drives this, and I'm going to run it. And based on everything that we've done before, which is previously whenever we just run the class definitions, nothing happened. Watch what happens right now. As you can see, not only did we get the singleton being initialized, but we also get the meta class initialized. What is interesting is that we didn't call anything. So what happens with metaclasses is that if you override the init method, it will be invoked when the class is loaded into memory. Notice that we haven't run any code here. This is the code that we would have run, but we haven't run this code. Now let's go quickly into the other eager implementation, which doesn't use init. It actually uses new. Let's remove this. and check whether the same thing happens here. And I'm just going to clear this. Let's run this right now and see whether this version, which instead of using init, it uses new, whether it will do the same. And again, it's exactly the same behavior. The only slight difference, if you notice, is that in this version, super is initialized first, and then you see the child being initialized. But if I go back into this eager implementation, and just remove this for a second, you can see that this is reversed. So this is very interesting. The most important thing about this, let me just clear this. The most important thing about this is that both of these implementations just use very similar logic to what we've seen in all the other singletons. What is different here is just the timing of the call. So notice that, for example, in this one, if you look at this one, for example, the first eager implementation, what we do is we have our instances just like before, and we override the init method. And in the init method, we set the instance and we put it into the instances dictionary. And then in the call, we simply return it. So just to prove that this is working, I'm going to run it. And as you can see, I am singleton, it's true. And if I go into the second implementation, let me just get rid of this. And if I go into this implementation, the idea is very much the same. Instead of init, we are overriding new, basically getting exactly the same thing, which is we initialize this instance before the class is ever actually constructed. In other words, eager loading. And if I run this, we get exactly the same as we had before. The only difference is just the order of the actual eager loading initialization. Okay, so this is it for eager implementation. Next, we're going to look at thread safety with our singletons. All right, so let's have a look at how we would implement thread safety in our singleton. What we have here is a very, very simple implementation. This is not a meta class-based implementation. All that we're doing here is we're taking the simple implementation of our singleton and we're making it thread safe. And the way you make it thread safe is you have to identify the critical section. And in our case, the critical section is when we're actually creating the instance, which would be here in the new method. We have an instance that has nothing. We create a lock, which is a threading lock. And then what we do is we acquire the lock with the with block. And once we have acquired the lock, we basically check, okay, if we don't have an instance, we create it. But otherwise, if we do, then we simply return it. And that's basically it. And now if we run it, of course, it's going to be exactly the same as before. This is still a singleton. The only difference is that this is a thread safe singleton. Okay, so what about doing it in a metaclass? Well, let's have a look at a metaclass implementation. Again, the idea is very much the same. We have our instances, we have our lock, and then in this case, we're going to get the actual instance for the singleton in our call method. Wherever we are actually instantiating the singleton inside the class, that's our critical section. So what we're going to do here is we're acquiring the lock, and then we do basically the same thing. If we don't have an instance, we create it and we add it into the instances dictionary. But if we have the instance, we simply return it. And that's basically it. So in this example, we have a little helper function, which is get singleton instance. It constructs a singleton, returns that singleton, and also prints the singleton's memory location. Next, we have an array of threads, and we create 10 thread objects, and we add them into that array. We append them into the array. At this point, the threads are not running. They're simply ready. They have been created. Next, we're going to run them. We walk through the array and we start all the threads. And then in this particular piece of code, what we're doing is we're creating a barrier, which is basically a piece of code that stops and waits for all the threads to finish. In other words, it will not go past line 39. If we had more lines here, like line 40, 50, 60, it would stop here and wait for all the threads to finish. And if I run this right now, what you would expect to see is the print statement being invoked 10 times. And here it is. Now, what you could do is you could go into the singleton class, where right now we just have a pass, which basically means that this is an empty class. And you could add something like, for example, printing time or something like that. I'll leave that as a little exercise for you to do. Okay, so I'm going to see you in the next lecture when we're going to look at some practical examples of a singleton pattern in action because we're going to create a logger. Okay, so I'll see you in the next lecture, and as always, keep on coding. All right, welcome back. In this lecture, we will create a utility logger and we'll make it into a thread-safe singleton. We'll go through a few iterations so that you can see the process of refining and refactoring the code. So in this first iteration, we'll just have a very simple logger. Note the following points. We are creating a named logger, which we simply name my logger. We do this so that we can tell the source of the logging. For example, in a different session, we could name the logger something else to differentiate the output from a different session. We also set the logger level to debug. Next, we set up the log data handlers of our logger. Think of these as destinations. So we create two destinations or two handlers. First, we create a file handler which will have as its destination my log file. This will be logged in the current code directory. We will also set the level of this destination to debug. Next, we also create a console handler which will write log data to the console, which is right here in our Visual Studio terminal output, and we'll set the level of this handler to info. We then define the format of our log entries. We set the timestamp and the name, which is the name of our logger, which is going to give us the source. Then we set the level with which the entry is logged, and finally, the actual log message. So the format of our full log entry is going to be timestamp, name, level, and the message. We then add this formatter to both destinations so that both the file and the console handlers use this formatter. So basically, both of them will output the same looking log data. And finally, we add these handlers to the logger itself. Okay, great. So this way we have finished our logger. As you can see, the code for running the logger is pretty straightforward. Now, let's run it and see what we get. And here you see the output. So first, you see the output here in the console. It's pretty straightforward. We have our messages and we have the levels. You can see the format. And here you can see the same output in our file. Well, actually, if you look at the output carefully, you can see that in the file, we have an extra message, which is the debug message. And the reason why we have a slightly different output in the file versus the console is because that's exactly how we have configured our logger. So if you go back and you look at the code, you will see that when we are creating the file handler, we're setting the logging to be debug, which basically means that this will log everything that is debug or above. But for the console handler, we're specifying that the level is info, which means that it's only going to log things that are info and above. And since debug is below info, that's why you don't see the debug level showing up in the console. So this is pretty great. But there are a few issues with this code and in general with this approach. First of all, this is not very object-oriented. In other words, this is not encapsulated and thus it is not really reusable. So to fix this issue, we'll do a couple things. First, we'll create a singleton version of this logger, and we'll also encapsulate the initialization of the logger into a function. We'll also make it thread safe to be absolutely sure that the singleton is reusable in all circumstances, even those involving multiple threads. Okay, so let's have a look at our new version of the logger. So as you can see, we have a singleton here. Now, this is not a meta class. We're starting with a very simple version. So what we have here is we have our instance, and in the getInstance method is where we ensure that only a single instance exists. We also make this singleton thread safe by using the lock and then ensuring that our critical section is properly protected. We also have an initialized logger routine where we encapsulate the logger creation logic. And this is the exact same logic as in our previous class. What we have done here is simply refactored it into this reusable method. Note that our logger is simply stored as an instance variable, which we named logger. And this is it. Now to get our logger instance, we go to the singleton logger class and invoke the singleton getInstance method, which returns our instance, and then we just access the logger instance variable and we use it. So as you can see, this is definitely better than before, but this is still not very elegant. And as you see, when we run it, it runs exactly the same as before. It writes to the console and it added some more entries into our file, as you can see from the different timestamp. But there are a few issues here. First of all, I do not like this singleton logger.getInstance.logger syntax. One simple solution would be to simply have the singleton logger get instance return just the logger. We'll fix that in the next iteration of our code. So next what we'll do is we'll refactor this code into a metaclass based singleton logger. All right, so let's have a look at a third iteration of our logger. So this is like the third version. Now the main difference here is that we're now using a meta class, but otherwise the code is pretty much the same as in the previous class that we have just seen. The main differences are as follows. We now have a singleton meta class in which we define the singleton logic as we have seen in the previous lecture. Of course, we also make it thread safe. Once we do that, we define the logger singleton class, which is in our case just the logger class. And we set its meta class type to be the singleton meta, which was defined just above. This is exactly what we did in the previous lecture. So what we do now here is we simply add the initialization code for the wrapped logger class in the initialize logger method. But note that we have made one simple improvement in the syntax. Rather than providing a logger variable to get the logger instance like we did in the previous example, here we return the actual logger instance through the getLogger method. So basically, we have our initialization, just like we did before. We have our initialize logger method. And then, rather than providing a logger variable to get the logger instance like we did in the previous example, here we return the actual logger instance through the getLogger method. So now when you look at how we actually use the code is just a little bit more elegant. Now what we do is we simply say logger is equal to, we get the logger instance, and then using the getLogger method, we actually get the proper logger instance, and then we use it exactly the same as before. And if we run it right now, as you see, it works exactly the same way as before. And if we go into our log file, you can see that a new set of messages has been added. But I am still not happy with this implementation for two reasons. I still do not like the fact that we need to get the logger through a getter. I don't like this logger dot and then get logger method. And also, I would like to make it a little bit more reusable by using some sort of a logger abstraction. In other words, I would like to use an abstract class to define some sort of a base logger. Okay, so let's have a look at that in the next and final iteration of our logger. Let me just get rid of this. Okay, so let's have a look now at the last one. So here is the final version of our logger adventure. This is our final version of the logger class. So we have made the following improvements. We create a new version of the meta class, which is based on the ABC meta class, which is basically an abstract base class. We do this so that we can create a nice, clean, abstract class based on this meta class. So apart from that, the singleton meta is exactly the same as it was before. It is just a straightforward meta class which defines the singleton logic just like before. But what we do here that is new is we now create a base logger class which as its meta type has the singleton meta class. This is a bit of a trick, but basically we have just made the base logger an abstract class. And you can see that we define 5 abstract methods which will be used for our logger. So let's have a look at the logger class. So now what we do is we define the actual implementation or the proper myLogger class, which does the following. First of all, it wraps around the logger instance, which in our case is the underscore logger variable. And what we do is we expose the inner underscore logger functionality only through the logging methods that are defined in the base logger class. And as you can see right here, we have the 5 logger methods implemented. So basically what we do is we wrap around the underscore logger instance, and then we delegate through our own methods, which is the debug, info, warning, error, and critical methods. We then delegate to the inner logger. So this is a pretty nice, simple implementation. Now, when you actually look at the syntax that we use, you can see that the syntax is pretty nice. All we do is we just say logger is equal to my logger, and then we just use it like any other logger before. We don't have to call any extra methods. So basically, what we have now is a singleton that is based on an abstract class, and the final class, which is my logger, follows the base class contract. So basically, we're following some good software engineering paradigms here. The nice thing about this contract for our base logger is that if I remove any of the implementations, for example, let's say I remove this. If I try to run it right now, watch what happens. You can see that it tells us that the abstract myLogger class is missing a method. So if I put that method back, the interpreter is smart enough to know that I have now followed the contract. So if I run this right now, let me just clear this. If I run this right now, everything is working exactly as it's supposed to be. Basically, mission accomplished. What we have here is a nice thread-safe singleton, which is based on an abstract contract. And if you go into the log file, you can see that now there are extra lines in our file. All right, so this is everything for this lecture. Please go through it one more time just to make sure that you understand everything. This is a pretty powerful design pattern. Next, what we'll be looking at is the factory method pattern. All right, I'll see you in the next lecture, and as always, keep on coding. All right, welcome back. Let's talk about some exercises that you can do that will solidify your understanding of the singleton pattern. All right, so exercise number 1, I would like you to create a singleton implementation which will generate a sequence of numbers to the callers. The idea here is that there is only a single number or sequence generator, so a single generator, and all the numbers follow a perfect sequence. So when we do a call to the generator using something like maybe a getNextNumber method, we should get the next number in the sequence no matter how we obtain the generator. So basically this way, it is kind of like a global generator. Then the next point would be to make that implementation both with eager instantiation and with lazy instantiation. And, ask yourself this question, which one would you prefer to use and why? Which one of them is just a little more efficient or better? Exercise number 2, I would like you to make the singleton that you created in exercise number 1 thread safe. Make it thread safe. Consider also the following issues. How would you test it? And how do you know it is properly thread safe? Okay, let's look at exercise number 3. Create a singleton implementation which will write to a common file, common meaning shared. Imagine that you wanted to audit all the actions in your application, so it's kind of like a log. It would make sense to log that information into a file with a guarantee that all callers, all clients, will write to the same file. And we also want to make the file configurable as to where is the file. For each call to the file audit manager, your code will generate a timestamp and will write the message entry into the file with a new line character at the end of each message. So it becomes to some extent human readable. Make that implementation both with eager instantiation and with lazy instantiation. And then again, which one would you prefer to use and why? Also, make your implementation thread safe. Alrighty then, good luck with these exercises, and if you have any questions, please do not hesitate to ask in the forums. As always, keep on coding, and I'm going to see you in the next lecture. Welcome back. Let's look into our second design pattern, the factory method pattern. Normally, we create objects using constructors. This is how you would create a rectangle by simply calling the rectangle constructor. This is what normal object-oriented programming languages do. But the question is this a good thing? The answer is no. In fact, this approach has a major architectural disadvantage. You have to know the exact class type you want to instantiate. Why is this bad? When you learn programming languages, nobody tells you, hey, don't use constructors. You use constructors. What if we wanted to create an app that used different types of shapes? What if the app was going to use shapes that we have not even thought of yet? How is that relevant? Let's look at a more specific scenario. Assume that you're creating a space shooter game. Think of maybe like an asteroids game or maybe Space Invaders or something like that. In this game, you will have different types of bullets that the user could use. But you do not know which bullets the user will want to use. So how do you create them? Additionally, you might in the future have new bullet types, so you might have types that you haven't even thought of yet. Typically, this is how you would instantiate your bullets. Let's say you have a fast bullet, so you create a fast bullet using a fast bullet constructor. The same thing goes maybe for a slow bullet. Maybe you have some sort of a splash bullet. As you can see, nothing wrong here. We're just using different constructors. And of course, we might have some sort of a bullet type in the future. We don't even know what it is yet. Maybe our users will say, hey, it would be nice to have this type of a bullet. And you'll say, you know what? I will add it to the game. Great. So what's the problem? The main problem with this approach is that your code is unnecessarily aware of the type of objects that it creates. And thus, it is strongly coupled with the type. So now let's look at the factory method. The factory method is a creational design pattern that lets us abstract out the creation logic of specific class instances. So it provides a mechanism for creation of objects without exposing the instantiation logic to the client. In our case, the instantiation logic is using the specific constructor. There are two main and crucial points in understanding this pattern. Objects are created by calling a factory method instead of calling a constructor. Also, objects are created through an abstraction, not a concretion. So, in the factory method design pattern, we create objects without exposing the creation logic to the caller. And the caller refers to the newly created object through a common interface. Going back to our bullet, if we make the bullet an abstract class, then we can make it to be the parent class of all bullets. Here's our bullet class, here is our fast bullet, here's our slow bullet, and here's our splash bullet. Each one of those is a bullet. So how does this help us? I mean, okay, sounds great, we're using some polymorphism here. Well, we can now create bullet instances based only on the bullet interface contract, instead of the specific bullet definition. We then use the factory method design pattern as follows. Here is our bullet factory, and it creates a bullet. It's pretty much that simple. At least the essence of the pattern is that you always return the contract interface. So the idea is pretty straightforward. In code, the caller will ask for a bullet instance based on some abstract name. For example, I could say my bullet 001 is equal to bullet factory.create some bullet based on some sort of an ID. So as you can see, we have two different bullets, and one creates a fast bullet, the other one creates a splash bullet. The nice thing is that at this point, we don't have to worry about how the bullet is created. That's hidden in the bullet factory. The main advantage is that the caller does not need to know how the factory creates the bullet. The caller only needs to know how to call the factory and with what initialization data. We could even make this more generic by using some type of context data to initialize the instance. For example, we could create some sort of a bullet build context, which has some initialization data, and then we simply pass that context to the bullet factory. One example advantage of using a factory method pattern is that we could cache objects in the factory for added efficiency. Here is the factory used without a cache, and here is the same factory but with a cache that is hidden behind the factory call, so the caller does not even know about this implementation. We could simply cache all the bullets so that your code could be much more efficient. The beauty of this is that the caller that uses bullet factory has no idea that there's a bullet cache. So where does the factory method pattern come from? This is yet another famous gang of four pattern, and its motivation is stated as follows. Define an interface for creating an object, but let subclasses decide which class to instantiate. Factory method lets a class defer instantiation to the subclasses. This pattern is often used with the following gang of four patterns. Strategy and iterator patterns are often used with factory method pattern to let collection subclasses return different types of iterators that are compatible with the collections. In this lecture, we're going to cover the strategy pattern, but you definitely can look up the iterator pattern. Factory method pattern can also be used in the object pool pattern when creating cached objects of different subtypes, as you've seen with the previous slide where we've looked at the possibility of having a cache sitting behind the factory. So when do you use it? When a caller can't anticipate the types of object it must create. Let's say you're coding a mobile game. The user can choose any weapon or a spaceship, but you do not know which one they will use. Another example is new types of spaceships or weapons can be added to the game in the future without any changes to the client code. Also, when you have many objects of a common type, like for example a shape with subclasses such as rectangle, circle, triangle, it's a perfect opening for a factory method pattern. When not to use. There is no specific restrictions as to when not to use it. What are the pros of using factory method pattern? It allows subclasses to choose the type of objects to create. It's simple to implement. It is simpler than builder pattern, which we're going to cover in the next design pattern we're going to go over. It also promotes loose coupling by eliminating the need to bind application-specific classes into the code. That means that the code interacts only with the resultant interface or abstract class. It definitely adheres to the single responsibility principle. You can move the creation code into one place, making the code much easier to support. Also, it follows the open-close principle. You can introduce new subtypes into the program without breaking existing client code. This results in architecturally very clean code. What are the cons? One disadvantage of the factory method pattern is that it can expand the total number of classes in a system. Every concrete class also requires a concrete creator class, but please do note that the parameterized factory method avoids this downside. Let's look at the design considerations. When you have many objects of a common type, like for example a shape, make all such object types, like for example eye-shape, follow the same interface or extend the same abstract class. This interface should then declare methods that make sense in every shape, but in a generalized way. For example, for a shape, we might have a method called draw or calculate area. Then, create a factory with a static creation method which always returns the same common interface reference. For example, like an eye shape or like what we had with the bullet. Also, let the factory know which instance you want through some sort of a constant ID for the specific object type. This can be accomplished through maybe an enum or a list of constants, which could be integers or strings. There are two main variants of this pattern. The very popular simple factory method variant, which is also called parameterized factory method pattern. We're going to mostly cover the simplified variant here as it is more useful for the majority of projects, but we will briefly mention the classic variant as well. The classic or the original Gang of 4 factory method variant. We will have a look at that one as well, but we're not going to cover that extensively. Alright, do not hesitate to ask any questions, and in the next lecture, we're going to go through the UML diagrams and the implementation details for how does one go about using the factory method pattern in real code. See you then. Welcome back. Let's have a look at the architectural diagram of the factory method pattern. As you remember from a previous lecture, there are two main variants of the pattern. We have the classic Gang of 4 factory method variant, and we have the very popular simple factory method variant, also called parameterized factory method pattern. Let's look first at the classic Gang of 4 factory method variant. We start with an interface that stands for some sort of an instance of a class that we would like to abstract. This could, for example, be shape, this could be product, and it has an operation. Here we have two concrete implementations of the instance interface, which we call concrete instance A and concrete instance B. Notice that both of them have defined the operation, which was defined in the instance interface. What we then have is we create a contract for a factory, which is going to create instances of our instance interface. For example, we would create a concrete factory A implementation of the factory, which would specifically create the concrete instance A objects. And we also create a concrete factory B implementation of our factory, which would specifically create objects of the type concrete instance B. For every concrete implementation of an interface, we have a concrete implementation of a factory method that will create that. So for example, instead of instance, if we had shape and our concrete implementations were triangle and rectangle, then our shape factory would have two implementations of the factory interface, which would be triangle factory and rectangle factory. That's the idea of the original Gang of Four factory method variant. For every concrete instance of the implementation of our interface, we would have a concrete factory implementation. This is how you would use it in code. We would like to get a concrete instance A. So what we would do, instance A, is we would use the concrete factory A, we would instantiate it, and then we would call the method createInstance, which would return to us the concrete instance A through the instance interface. If we wanted to get concrete instance B, then we would have to call the concrete factory B to create that instance. Let's say that our client would like to get an object of the type concrete instance A. What the client would do is it would call the concrete factory A createInstance method, and that concrete factory A would then hide the implementation of how it actually creates the concrete instance A. And the same thing would work for any other instance. How is this different from the simple factory method variant, which we also call parameterized factory method pattern? There's actually a huge difference. We start with the same idea that we have some object that we would like to create. We abstract this object through an interface. In our case, we have instance with one operation. And we have two concrete implementations, concrete instance A and concrete instance B. The main difference, though, is that in the simple factory method variant, we do not have an interface for our factory. We have an instance factory. We have one factory for all the different instances that we would like to create. Notice also that we have a private constructor, so you cannot instantiate this factory, and we have a static createInstance method, which takes a parameter. That parameter could be anything really, but in this example, it's going to be the name of the class that we would like to instantiate. Here's a UML diagram. Our client would like to create a concrete instance A implementation. So what it does is it calls the instance factory static method createInstance. It passes a parameter, which in this case is a name, instance A. The instance factory has a switch statement behind the scenes where it basically matches the name against how it should create the instance for you. In this simple example, we just have a simple switch, and if the case happens to be instance A, then it creates specifically a concrete instance A object. If you passed instance B, then you would get a concrete instance B object. The idea is basically that as a client, I don't care how the object is created, I would just like to get the specific object I'm interested in. And the way you would do it in code is pretty straightforward. If you wanted to get instance A, you call instance factory createInstance with the parameter the instance A. If you wanted to create instance B implementation, you would call instance factory with the parameter instance B. So the nice thing about this as compared to the original one is that we only need one factory, and we call the factories method with some sort of parameters, which allows us to even expand this, as you will see later on in code, so that we can actually provide some sort of a context and provide more information to the specific class. In this course, we're going to use the simplified variant, which is this one, as it is more useful for the majority of projects. Alright, so this is everything for this lecture. In the next lecture, we're going to be looking at some code for the simple factory method. See you then. Welcome back. In this lecture, we will be looking at some code of factory method pattern in action. So let's run this code first. As you can see, this is a very simple game-like implementation of displaying different shapes when the user clicks on the screen. The shapes are randomly generated as follows. We generate the random shape type. We currently have rectangles and circles. And then we also generate a random color for the shape, as well as the size. Okay, so let's look at the UML for the first iteration of our code first. We have an abstract shape class, which has two instance variables, x and y, which are the location of the shape in the coordinate system. We will use this when we display the shape. This will be the location of the user's mouse click. Okay, so what makes this class abstract? It will be the draw method, which will be implemented by each shape child with a specific shape rendering, so that, for example, the rectangle will draw itself as a rectangle and a circle, for example, as a circle. We also have these two specific implementations. We have a rectangle and we have a circle. We also have a shape factory, which will isolate any client code from the specific knowledge of how to create a given shape. The whole point of having a factory is to abstract the object creation process. Note that the factory returns just a shape contract. Okay, so now let's have a look at the code itself. So we have our shape abstract class with the abstract draw method. We also have two derived classes. We have a circle and we have a rectangle. Note how each class implements the draw method that is specific to its own shape. Some of the important things to note are the following. Each shape is responsible for its own random data generation. We have random color generation and we have random size generation. And this is, of course, according to each shape. So a circle will generate the radius and rectangle will generate the width and height. So we're delegating the random generation of data that is specific to the shape itself. Next, we have the shape factory. This is a parameterized factory. In other words, this is the simple version. And what it does is pretty simple. It accepts a shape type, which is a string name such as circle or rectangle, and it also accepts the location of the shape. It then returns the specific shape back to the caller. This is very flexible since it allows us to not only create the shapes easily, it also allows us to place any pre and post conditions on the creation process. For example, we could not allow any shapes that have been created off the screen. That's just one example. And notice that we also have an exception if there was an invalid input to our factory, such as, for example, an illegal shape. So one can say that this fully creates the factory method pattern. Now let's have a look at what the code actually does. So in the main, what we're doing is first we initialize the Pygame environment. We set the display size to be 800 by 600 pixels, which defines our output window. Then we create a clock variable, which will be used in our game loop to generate the update ticks with a specific frequency. You will see that in a second. Next, we create our shape factory as an instance for ease of use, even though we could directly use it because it's a static method that we're using. We also have an array, or list if you will, of all our shapes that were so far generated in this session. We need this so that we can re-render all the shapes at each game loop iteration. We also have a simple flag which controls if the game loop is running or if we're done. The main engine of this particular little code is a game loop. A game loop is just an infinite loop that quickly iterates over specific code. This is done for two reasons. First of all, we can quickly render any changes to our data since at each iteration of the loop, we re-render all the screen data. And also we can listen for any data changes in real time with each loop iteration. And in our case, we'll listen for the user's mouse click. So first, we process any events that are happening in our environment, and we really only care about a mouse click or the quit event. Our main interest, of course, is in the mouse click event. We specifically wait for a mouse down event. When that happens, we get the position of the click. We then randomly generate the shape type, and we ask the factory to create the instance of that specific shape with that data. Once the shape has been generated, we add it to the list of shapes we have so far generated. We then clear the screen, and this is a preparation for a redraw or a re-render of the entire Pygame window screen. What you see here is basically a white color that we will repaint the screen with. Then we go through each shape in our shape list and we call the draw method for each shape while passing to the shape the screen variable, which represents the drawing surface. Notice that at this point, the draw method hasn't really drawn anything yet. It has actually just created that in a buffer. We then force the screen update with the flip method. Finally, we set the refresh rate to be at most 60 frames per second And we do it for a number of reasons. First of all, we do this to control how smooth the refresh rate is by basically controlling the loop's iteration frequency. And basically by calling the clock.tick60 at the end of each iteration of the game loop, we ensure that the loop runs at a consistent 60 frames per second. Let's run the code again, this time with the explanation in mind. So the loop is running right now, rendering the surface at 60 frames per second. So what you see right now, even though it doesn't look like anything is happening, you have the game loop redrawing the whole window with white color at 60 frames per second. It also checks if there is any shapes already drawn, which would be saved in our list. And if yes, it draws each shape into the buffer. If I click on it right now, this shape has just been added to the buffer, and it was rendered, and it's being rendered right now 60 times per second. In the same loop, the mouse down event is being monitored, and if the user clicks on the screen, then the shape is randomly generated and added to the list of shapes. At the next iteration of the loop, it will draw the screen white and then redraw all shapes, including the one just generated. As you see, I'm clicking a few times. It gets saved, it is re-rendered. At the same time, the loop is checking whether the user is clicking, and this is just constantly happening. Okay, now back to the factory method pattern. How good is the code that we have? If you examine this code and the UML, you will notice that the shape factory is not very flexible. Have a look at the create shape method. It is literally baked in when it comes to its parameters. If at any point we wanted to change something about the parameters, we would have to change every single client call in our code. So now there's a better way. What we can do is we can use a context class, which will simply aggregate all the data necessary to create the given shape. Okay, so let's look at the improved UML diagram. The change is relatively simple. What we do is we add a new class, shapeContext, and we will use this class as the input to the createShape method. So in other words, we're encapsulating the input into one parameter. In general, this is a better way of passing data to a factory method, as it allows also for more flexibility with required versus optional variables, for example. This is really a small change, but it adds flexibility to our architecture, and the rest of the code stays the same. So let's have a look at the change. And as you can see, here's our shape context class, and here is the shape factory, which now uses the context information. And if we run it right now, you can see that the code runs exactly the same as it should. What we have done is we have refactored the code to make it more architecturally flexible. Okay, so this is really it for the factory method pattern, but before we go into the next design pattern, I would like you to think about the following aspects of our code. First of all, can we move the color from each of the shape implementations, which is the circle and the rectangle, and move it into the base shape class? Number two, could we improve the way each class generates the random data? And number three, notice that we use just a normal string when we're comparing the shape type in our factory. You can see that we're basically just comparing it to a circle string and a rectangle string. That's pretty bad, actually. That's not a good way of coding. First of all, not only could you have a lot of typos, but you also have to keep on chasing where your constants are. So what I'll do is I'll leave those for you to think about and experiment with, but I will make one final code change. We're going to use an enumeration. In other words, we're going to fix that third problem, which is just using a normal string. So let's have a look at the updated piece of code. So here's the code. And first of all, notice that we have added an enumeration. And if you want to use enumerations in Python, you will need to import the enum and auto from the enum library. Now, what we're doing basically is we define two types that we need right now. We can easily add new ones later on. And this is very safe to use as you eliminate any kind of typos or spelling mistakes. Note also how the shape factory uses the enum. It's much nicer and cleaner code. But the main advantage is how we generate the random shape. Note that we now have future-proofed our generation code. So before, we basically used this. So let's have a look at the code before. So before, you can see that To generate the shape, we did this. Shape type is equal to random choice, and then we just create an array or a list of currently known types. But if you look at the code in number 3, you can see that in the improved code, we're basically just creating a list of shape types. And this is very nice because this code will not change no matter how many new shapes you create. You can see that now our shape type is just a random choice from a list that already pulls the data, and it's also pretty elegant. Here is the updated UML, where you can see the enumeration being used. And please do the exercises provided next, and then I'll see you in the Builder Design Pattern introduction. See you then, and as always, keep on coding. Welcome back. Here are some exercises for you, and these are for the factory method pattern. These are coding exercises. So exercise number 1 is create an abstract class called spaceship, which will simulate a spaceship for a video game. You can assume such simple properties as position, size, display name, and speed. Position would obviously be the location of the spaceship on the screen, so this would be an XY value. Size can also be expressed in terms of XY or width and height. Display name would be simply the name of the spaceship, and speed, you could give it as a scalar, like for example 10, but usually this is given as a vector, which would again be as an X and Y. Next thing you will do is you will create a number of concrete classes which are going to extend spaceship. We'll have a Millennium Falcon, we're going to have a UNSC Infinity, you will have USS Enterprise and Serenity. The Millennium Falcon is Star Wars, USC Infinity is from the video game Halo, USS Enterprise is Star Trek, and Serenity would be from Firefly. Using the simple factory method, create a factory implementation that will create each one of those instances. And simple factory method pattern simply means you don't have to do a lot of abstractions. Now, for exercise number 2, you can try to implement the exact factory from exercise number 1, so exactly the same functionality, but this time using the classic factory method pattern. This basically entails that you need to create a specific factory for each of the concrete spaceship class types. So, for example, when you need to create USS Enterprise, you will in fact delegate to a USS Enterprise factory. This means that the creation will need to be done in some sort of a switch to sort out which factory to use. Okay, so this is basically it for these exercises. Give them a try, and if you have any questions, do not hesitate to ask. And as always, keep on coding. Welcome back. Let's talk about the builder design pattern. It's a very important design pattern to put into your arsenal of architectural design patterns. Builder is a creational design pattern that is used to encapsulate reusable logic of building complex objects. What do we mean by complex objects? Those are objects that are made up of many distinct parts. Those are objects with a well-defined relationship between those distinct parts. So it's not just a bag of loosely related objects. Normally we have some sort of a good design that creates a complex object. The main tenets of this pattern are: you want to separate the construction of a complex object from its representation, and you want to design it in a manner so that the same construction process can create different representations. This is very important, as we're going to see in the next slide. Consider the following scenario. Imagine that you're coding the process of building a house for a video game with the following attributes. We have walls, we have windows, we have floors, we have a garage, we have a swimming pool, we have doors, backyard, a garden, basement, and maybe other things as well. This is obviously a complex object that is made up of many other objects. So one can think of this as having an object hierarchy. One way to design this object is to create a house class with a very long and complex constructor, something like house, and you see all those parameters. So for example, we could look at that as we would like to build a house with 10 walls, 10 windows, 2 floors, 1 garage, no swimming pool, 5 doors, no backyard, no garden, and no basement. The problem with this is that a code like this would be ugly and quickly would become unreadable. It is very inflexible, and most importantly, it's difficult to maintain. The crux of the problem, the reason why we have this problem here, is that the object, the house, creates itself. We have the object representation, which is the house itself, and then we have the object creation. The problem here is that house also has the responsibility of creating itself through the constructor. So what should we do? We want to extract the object construction away from the class representation. In other words, we do not let the object create itself to the user. We want to abstract the creation process. So how do we do it? We use the builder pattern. It hides the process of building complex objects. A builder is an object that is able to construct other objects. It constructs and assembles different object parts to build the result objects. But the builder pattern is much more than that. The builder pattern is not just about encapsulation and hiding of the creation process. It is also designed for reusability and flexibility. A builder organizes object construction into a set of processing steps. Step 1, for example, could be building the walls. Step 2 could be building a pool. Step 3, or any other step, would be something else. And finally, we might have the end step, which would be build a roof. To create an object, the builder is instructed to execute a series of these steps. This is what is at the heart of the builder pattern. But do we have to always call all those steps? The answer is no. The strength of the pattern lies in that we don't need to call all of the steps. We can design the builder to only call those steps that are necessary to produce a particular configuration of the object. This is great flexibility. Consider another simple scenario. Imagine that you have a document, for example, a rich text format document on your hard drive. To view it, it has to be loaded, and then it has to be constructed. We can imagine the following workflow. You have the RTF document. The document then is read by a reader, which creates a number of tokens. These tokens then are passed onto a parser. A parser then parses the tokens into elements. The elements then go into a builder, and a builder can create a Google document, it can create a Word document, it can create an HTML document, or it can create a PDF. That's the beauty of this workflow. Here is a bit of a pseudocode for it. For each element that we parse, we can switch on the element type. For example, if the type is a title, then we have the builder create the title. If the type is a page, we have the builder create a page. If the type is author, we have the builder create the author. The idea again here is that the builder executes a number of distinct steps in order to create the larger object, which is the document in this case. But the builder gets even better. We can create variants of the builders to produce slightly different version of those steps. In fact, the previous example needs to be expanded. This is what we had before, but what we really have is this. We start with the RTF document, we go into a reader, we then generate the tokens, then the parser creates the elements, and then we have a special step or a special controller called the director. What the director then does, depending on the type of document that we would like to view it as, let's say if it's a PDF or HTML, the director then is going to delegate it to a specific builder. So we might have a Google Doc builder, which is going to create a Google Doc. We might have a Word document builder, which is going to create a Word document. We might have an HTML builder, which is going to create an HTML document. And we might have a PDF builder, which is going to generate a PDF document. So you can see that the idea of the builder pattern is that we have some sort of a director that then delegates to the specific type of builder that we would like to use. Notice the synergy. All of these builders will follow the same steps because they are all creating documents, but obviously the construction of the documents is a little different for each document. This is an important Gang of Four pattern, and its motivation is stated as follows. Separate the construction of a complex object from its representation so that the same construction process can create different representations. That is exactly what we have seen in the previous example. The pattern is often used with the following Gang of Four patterns. It's used with the composite pattern when you're creating tree-like aggregations of objects, and oftentimes you will implement your builder pattern as a singleton. When do you use it? When you have a complex class with many constructors. Because the builder pattern lets you build your objects in a step-by-step manner, you can skip some steps if they are not needed. Also, when you have to build complex composite tree-like objects, and also when you want to build different representation of your complex object, but still use the same general steps. That's exactly what you have seen in the example with the document. When not to use. There is no need to use this pattern for simple objects. At that point, you can just use the factory method for those. What are the pros? First of all, it provides clear separation between the construction and representation of an object. It provides finer control over the steps of the construction process, and it supports changing the internal representation of objects. What are the cons? A distinct concrete builder must be created for each type of object, so it increases the number of classes that you have. Builder classes must also be mutable, and it may complicate dependency injection if you happen to dynamically generate certain elements of your code. What are the design considerations? You should encapsulate creating and assembling the parts of a complex object in a separate builder object. Create a specific class, a director, which will delegate object creation to a builder object instead of creating the objects directly. Look for synergy in the family of the objects that you're modeling. You should be able to use the same construction process by delegating to different builder objects to create different representations of a complex object. Think of different types of houses or documents or pizza orders or, for example, cars. All of these can slightly be different, but the construction will still follow the same steps. Next, we're going to look at the architecture of the builder pattern. See you then. Welcome back. Now that we understand the need and motivation for the builder pattern, let's go over its architecture in detail. Imagine that you have a product. You would like to use the builder pattern to create the product. So you have an abstract product class, and let's assume that you have two implementations of the product, product 001 and product 002. The next thing that you're going to do is you're going to create a builder abstraction, which is going to build a product. It will have a method called, for example, getResult, which is going to be the final build of what the product is. And you're going to have the necessary steps to build any given product. In this case, we have built part A, part B, part C. It might vary from product to product. So some of the products might actually not include one of the methods. For example, build part A could be empty. But the important thing is that you abstract the builder interface. The next thing that we do is we create concrete builders. So we might have a concrete builder 001 and we will have a concrete builder 002. Notice that each builder creates the specific product, but it returns in the getResult an actual product abstraction. This is important. So now that we have this, what is the next step? We need a director. Notice that the director aggregates the builder. And there are two ways in which we can initialize the director with the builder. We can either initialize the director specifically when we're creating the director with a given builder, or once we have created the director, we can use the change builder method to move from one builder to another. And notice that we have a method for the director called construct, which, given whatever the current builder is, will construct a product based on that builder. So basically, the way internally the director would do it is the director would simply go through all the different parts. So it will call build part A, part B, part C, and then that would return the result. This is a pretty straightforward way of looking at the builder pattern. Now let's have a look at the sequence diagram. The sequence diagram would look as follows. We have a client, we have a director, and we have a concrete builder. What the client does is it will first create the concrete builder. It will then assign that builder to the director by using the change builder method, and then it will simply call the director's construct method to create the specific product. The director simply calls build part A, build part B, build part C, and then it returns the full result, which is the product, back to the client. Note a few things. The client is aware of what type of product they want. So they initialize the director with a specific builder product, which is completely fine. The director calls all the specific methods of the builder in a predefined sequence, but it does not know anything about the product. It simply just calls the methods one after the other. If you wanted special logic per product, then you would need to code this knowledge into the director or somehow code it into the builder. Notice that all the builders have exactly the same method, build part A, part B, part C. If for some reason a builder doesn't need one of the parts, then all you need to do is just implement that as an empty method. All right, so now let's look how we would model the following using the builder design pattern. You remember that from the previous lecture. Let's see how we would model the director and the builder part using UML. So as before, we have a document abstraction. Next, we define the document builder. In our case, the document builder is going to have a create title, create page, create author, etc. And then we also have a getResult method, which returns the full document. Next, what we do is we define the different builders that we want for the types of document. So if we have a document that is a Google Doc, we'll create a Google Doc builder. If we need an HTML document builder, then we'll create that as well. And ultimately, in the end, the document director is pretty straightforward. Just like what we've seen in the previous diagram, the document director is going to aggregate the document builder. You can change which builder you're using depending on the type of document you're trying to create. And then all you do in this case is call the getDocument method, which invokes all the necessary methods to create a particular document and returns that document to you. So hopefully this is a little clearer right now. I know that the previous lecture was pretty fast and pretty compact. So hopefully this architectural overview has given you a better idea of what to do here. All right then. Next, what we're going to do is we're going to actually look at how to code the builder pattern in Python. See you then. Welcome back. Let's have a look at a relatively simple builder design pattern code. So let's have a look at the UML diagram first. A developer's favorite, which is pizza. So what we're doing basically is just have a very simple builder for different types of pizzas. So let's have a look at, first of all, our pizza object or our pizza class. And as you see that the pizza basically just holds things like toppings, fries, name, size, as well as crust and sauce. And you can see we have enumerations for those. Like, for example, we have pizza sauce as tomato, garlic, hot or mild. Pizza crust could be classic, deep dish. And you also have pizza sizes in small, medium, large. So that's pretty straightforward. So what we have is we have an object, which is a pizza. Then what we have is we have an abstraction of the pizza builder. And what a pizza builder does is it creates a pizza. Notice that we have a number of concrete methods like create pizza, get pizza, set pizza price, and set size, and add notes. But we also have three abstract methods: build sauce, build topics, and build crust. That's really what builds a different type of pizza. We have two concrete builders. We have a New York pizza builder, and we have a Hawaiian pizza builder. And notice that each one of those implements the three methods: the build sauce, build toppings, and build crust. Okay, so that's pretty straightforward. You can see that the pizza builder creates a pizza. Now let's have a look at the pizza director. What the pizza director does is it basically aggregates a pizza builder. You can then set a pizza builder, and then you would call make pizza and then get pizza. And of course, internally, what the pizza builder does is it calls the build sauce, build topics, and build crust methods for whatever pizza builder has been put inside. So that was UML. Let's have a look quickly at the actual code. So what I'm going to do is I'm going to run it first so that you can see it's just a very, very simple UI. If I click here, it's going to build our pizza. So what I have done is just I'm kind of alternating between New York and Hawaiian. So if I click plus right now, you can see that a delicious New York pizza with New York crust covered in mozzarella cheese and pepperoni has been created. We also output that to the debug console. If I click it again, it's going to now create a Hawaiian pizza. A delicious Hawaiian style pizza with classic crust covered in ham and pineapple. So if you now go back into our let's have a look at an outline. If you go back right now into the code, you can see that in our pizza.dart, we have our enums, which is the pizza size, pizza sauce, and pizza crust. We have our pizza class, with some business functions and some getters. And we also have a simple stringify method so that the topics, which are just strings, can be nicely concatenated for better formatting. And we also have overridden the toString method for our pizza. That's merely just convenience so that we can output it, for example, to the screen so you can actually read it. Now let's have a look at the pizza builder. The pizza builder is an abstract class. It aggregates a pizza. We made it protected, and it also has a string name. In the create pizza, what we do is we create a new pizza object, and then we set the name of that pizza. You can also get the pizza, you can set the pizza price, you can set the size, and you can add notes. These are all specific things that have nothing to do with the pizza building. It has to do more with initialization of the builder. Now, at the heart of the builder, we have these three abstract methods: build sauce, build topics, and build crust. So let's have a look quickly at what the Hawaiian pizza builder does. It extends pizza builder so it gets all the implementations of the concrete methods, but we also override the three abstract methods from the pizza builder, which is build crust, build sauce, and build toppings. And as you can see, all that we're doing here is, first of all, the Hawaiian pizza builder, the name is Hawaiian style, the crust is classic, the sauce is mild, and the toppings are simply ham and pineapple. So as you see, what the builder does is it takes each step of the building process and adds the specific implementation details for that particular, in this case, pizza. If you look at the New York pizza, it's exactly the same idea. We put the crust as New York, sauce as tomato, and then mozzarella cheese and pepperoni. And then we have the pizza director, and all the pizza director does is it aggregates the pizza builder, and it has a method called make pizza. And notice that the make pizza simply delegates to the pizza builder by creating the pizza, building the crust, building the sauce, and building the toppings. And that's really it. This is a very, very simple example. It can get much more complicated, but I would like you to understand here the relationship between the director and how the pizza builder abstraction is created. Notice also that, of course, pizza could have been an abstract class as well, but it was unnecessary here. In more complex scenarios, imagine you have a document creator and you need to create different types of documents. Then not only will you have a different builder for each document, you will actually be creating different documents. So in that case, your document, which is what your builder would be creating, would actually be an abstract class, which you then extend. How is this actually driven? If you go into main.dart, you can see that all that we're doing is we're creating a pizza director. We then create two concrete builders. And then what we do is we build the Hawaiian pizza, for example, by setting the pizza builder for the director as being Hawaiian pizza builder. Then we just make the pizza and then we get the pizza. And the same thing for the New York pizza builder. All right. Next, we're going to go into the adapter design pattern. I'll see you there. Welcome back. This is going to be a set of coding exercises for builder pattern. All right, so exercise number 1 is going to be create a simple user class which holds the following data: first name, which is required, last name, which is required, age, which is optional, phone number, which is optional, and address, which is also optional. You can keep all of these as simple values. So first name, last name, phone number, and address can be strings, and age can simply be an integer. You'll also have an email address, which is also required. Make all these elements immutable in your user class. Provide only getters. In other words, once the user class has been initialized and instantiated, you should not be able to change any of that data. Next, create a user builder class that can build a user with the above elements and which then can be used to initialize the user class. Good luck. If you have any questions, do not hesitate to ask, and otherwise, I'm going to see you in the next lecture. And as always, keep on coding. Welcome back. Today we will tackle the adapter pattern. Let's start this lecture with 2 simple scenarios. Imagine that you have some investments and you have a provider class which allows you to track your investment by sourcing the investment data in XML format. But since it is always better to visualize things, you would like to see some investments charts. So you also have a charting class, which creates a visual representation of your investment data. But unfortunately, this charting library class only accepts data in JSON format. Let's see what the problem is. Here we have our provider, which generates XML data output. And here we have a JSON data sync, which is the data format for our charting library class. The problem is that the two data formats are not compatible. So this is an example of data incompatibility. One simple solution would be to rewrite the provider to generate JSON data, but you could already have a lot of code that depends on the XML output. So rewriting this class is not a good idea, and it also violates the S.O.L.I.D principles. But there is a better and more maintainable way of doing this. Before we do that, let's look at the second scenario. Imagine that you have some shape libraries, and in there you have a legacy rectangle code which uses the following constructor. Basically, it's a rectangle xy_wh which defines a rectangle based on its xy position and its width and height. Now, let's say that your code needs to start using a new version of rectangle which has the following constructor. Rectangle x1, y1, x2, y2, which defines a rectangle based on its x1, y1 upper left corner position and x2, y2, which would be its lower right corner position. These two representations are both valid for a rectangle, but the definitions are not compatible. This is an example of interface incompatibility. We could rewrite all of our legacy code to work with the new rectangle, but this could mean lots of code changes. There is a better and more maintainable way. Okay, so how do we deal with these issues? You guessed it, we have a design pattern for it. To solve these incompatibilities, we can use the adapter design pattern. The UML for the diagram is not very complex. Adaptee is the service we want to use. For example, the charting library or the new rectangle interface. iTarget is the interface that our own code uses. We abstract it out into an interface. Finally, the adapter is the wrapper which will allow seamless conversion between the iTarget and the adaptee. Here is the definition. An adapter is a structural design pattern which is used to convert the interface contract of one class to be compatible with another. Structural in this context means that this design pattern deals with issues of structure of interfaces and/or objects. The conversion that this pattern deals with can take two different elements into account. First, an adapter can convert source data into formats that the client can understand. In the case of the investment provider, we're converting from XML, which was our source, into JSON, which was the destination for the client. Here we see the provider which generates XML data, and here we have the client. Charting library, which only accepts JSON data. The adapter would reconcile the differences by accepting the XML as input and providing the corresponding translated JSON as output. So this example deals with adapting data formats. The other scenario is that an adapter can help objects with different or incompatible interfaces collaborate. Here we see the legacy rectangle mentioned in our second scenario, and it has this specific initialization interface which accepts XY position and then the width and the height of the rectangle. And we would like to adapt the legacy code with a new rectangle definition, which uses positions x1, y1 and x2, y2 to define the new rectangle. The adapter in this case would accept as input the legacy interface and would transform that into the new rectangle input, which would then be fed into the new rectangle definition. So where did adapter come from? This is, yet again, a very useful and classic Gang of Four pattern, and its motivation is stated as follows. Convert the interface of a class into another interface that the client expects. Adapter lets classes work together that couldn't otherwise because of incompatible interfaces. So how does adapter pattern relate to other Gang of Four patterns? We have bridge, state, and strategy patterns which are based on composition, which means that they delegate work to other objects. Adapter pattern also relies on composition, so sometimes it might be hard to decide which pattern to use, but each of these patterns attempts to solve different problems. In other words, they have different motivations. Note that, in essence, the adapter pattern provides a different interface to the wrapped object. Some other gang of form patterns that are sometimes similar to the adapter would be a proxy, which provides the exact same interface, and decorator, which enhances existing interface. All we have to remember really is that the adapter adapts one interface to be used by another. So when should we use the adapter pattern? Use it when you have an existing class or contract that you would like to reuse, but its interface is not compatible with the rest of your code. When should we not use it? In general, if you can, use the adapter pattern, but if your code is very time sensitive and adding an extra layer of code would slow you down because of the overhead that the extra layer creates, then you might reconsider and rewrite your original code. So, what are the benefits of using the adapter pattern? You can separate data conversion from the main business logic of your application. This follows the single responsibility principle. In other words, you can use adapters in your architecture as a starting point for data exchange. And if a new data exchange protocol is needed, you just add a new adapter. You can also introduce adapters into your code without breaking any existing client code. This follows the open-closed principle. What about the cons? The adapter pattern can increase the overall complexity of your code since you are introducing more interfaces and classes. But in my opinion, this is a small price to pay for the convenience of good code abstraction that adapter pattern gives us. Okay, next we're going to look at the architecture of the adapter pattern. So how do we go about designing an adapter? We can break it down into easy-to-follow steps. First, identify the service, the adaptee, that you want to create an adapter for. Next, you declare the client interface and define how the client will communicate with the service. You then define the adapter class by implementing the client interface, but for now you can leave all the methods simply stubbed, not implemented yet. Next, you will add a private field to the adapter class to store the reference to the adaptee object. Next, you're going to implement each of the methods of the client interface in the adapter class. The adapter should internally delegate most of the actual work to the service, which is the adaptee object, handling only the interface or data format conversion. Finally, you need to make sure in your code that all your clients always use the adapter through the client interface that was declared in step 2. This will let you maintain the adapter code without affecting the client code. Let's have a look at an example. How would we create an adapter for this? Our first step would be, let's identify the service. Here, the service would be the charting library. Let's assume that the class is called charting library and has a single method called display data that takes in a JSON string. That will be our adaptee. The next step would be, since our provider gives us data in XML, we will define a simple iChart renderer interface that has a single method called display investment data, and it accepts an XML string. This is our iTarget. Next, we'll define the adapter class by implementing the client interface. That is our charting library adapter. Note that we have also added inside this adapter a private field to the adapter class to store the reference to the adaptee object, which in our case is the charting library class reference. Next, we would implement the data conversion algorithm inside the display investment data method in our adapter. We simply convert the incoming XML data string into the outgoing JSON data string, and we delegate the rest to the adaptee by calling the displayed data with the JSON data that we got from the conversion. Of course, in our code, we will then have to make sure that all our clients go through the iChart renderer interface whenever they want to talk to the charting library. But the important thing here is that the caller of the iChart renderer interface has no idea that they're calling the charting library. That's the beauty of this pattern. All right, so this is it for this lecture. Hope you've enjoyed it. Next, we will look at some Python code that showcases implementation of the adapter pattern. See you then. And as always, keep on coding. Welcome back. Let's have a look at some sample code for the adapter design pattern in Flutter. Let me run the application first. It's a very simple application. It deals with personal contacts, and we have a menu here which shows XML contacts, JSON contacts, and CSV contacts. The CSV part, the comma separated values, will be for you to do as an exercise when you're writing your own adapter into this framework. If I choose XML contacts, what it does is it brings a list of all the contacts that we have. The little green thing shows that they're a friend. The amber shows that they're not a friend. This is just really a very simple UI. The point of this demonstration is just to show how the adapter pattern works. So we have John Smith. I just put XML here so that you know what the source was. If I get out of this right now and go back and load, for example, JSON contacts, it's basically the same thing, same idea. We load the name of the person, the email, and the phone number. And this shows you that this is a friend, and this shows you that it's not a friend. Okay, so what exactly are we doing here? Let's look first at the actual UML for this. So what you're seeing here, first of all, is we have our data, our contact data, which has a full name, email, phone number, and information about whether this contact is a friend or not. What we then have is we have two readers. We have an XML contacts reader and we have a JSON contacts reader. These two readers deal with different data formats. We don't want to be dealing with different data formats, so we would like to create adapters that are going to go around them that will always give us the same format of data. So what we're going to do is we're going to create an iContacts adapter, and that has one abstract method, which is getContacts, which returns a list of the actual contact data. So in order for that to happen, we're going to create two adapters, one for the XML contacts, the other one for the JSON contacts, and we're going to use the readers as the adaptees within the adapters. So let's have a look right now at how this works in code. So we have our class contact here. We then have the definition of the iContacts adapter, which is an abstract class. We then have the XML contact adapter, but first let's have a look at the actual reader. So here is an XML contacts reader. It's basically just mock data. So we have a number of simple XML records inside it, and we have a method which is getContactsXML, which returns the XML as a string. We have exactly the same thing for the JSON, which basically again mocks the JSON data, and it returns a JSON version of our contacts. So we have completely two different formats here. And again, the contacts JSON, it also just returns a string. Ultimately, these two readers don't know what it's going to be used for, so they're just returning a string version of their data. So these are our adaptees. So now let's have a look at the XML contacts adapter. So the XML contacts adapter, what it does is it implements our iContacts adapter interface or abstract interface. And then it has the reader, which is the adaptee. And then what it does is it implements the getContacts method, which is our contract method. It gets the contacts from the XML, and then we have a special parse method, which is right here, which parses the data the way the iContacts adapter stipulates. So it creates a list of contacts. If you look at the JSON, it's exactly the same idea. We have the adaptee, which is our JSON reader. And then inside the getContacts method, we simply get the data from our adaptee, from the reader, and then we parse it and we create the exact format, which is the list of contacts that the abstract interface for iContacts adapter stipulates. This is basically it. And in here, we just have two simple UI list representations. You can have a look at that. And then in our main Dart, all we do is we just define the menu. So really this here, this particular file, contacts.dart, has all the necessary information. All right, so this is it for this lecture. Please go over this code and have a look at the exercises, and I'm going to see you in the next lecture. And as always, keep on coding. Welcome back. Let's have a look at exercises for you to code the adapter pattern. So exercise number 1 is add an additional adapter to the lecture code, which will provide a conversion from CSV format to the format that we render. The CSV format is simply comma separated value, which is a file that has strings separated by newline, and each string, which forms a record, has its values separated with commas. To do that, come up with your own test SCV format that your code will be able to read. Parsing the CSV should be relatively easy with Dart's string functionality. What you really need to do is just split the file data against new lines, and then for each record, you need to split it with commas. Test your adapter with the existing code by making sure that your adapter can properly read and convert the CSV data into the format that our code requires. Exercise number 2. Consider the legacy rectangle provided in the adapter pattern lecture. Create an adapter which will take the legacy rectangle and convert it into the new rectangle signature. Legacy rectangle class uses the following constructor. As you see, it's a rectangle with X and Y and WH. The X and Y is, let's say, the lower left corner of the rectangle, and then width and height are simply the width and height of the rectangle. The new version of the rectangle class uses the following constructor: xy, y1, x2, y2, which is basically the lower left corner and then the opposite upper right corner. So you should be able to convert these two. So remember, the key point here is that you have a rectangle already, which is the legacy rectangle, which needs to be adapted to the new signature so that your new code can use that. All right, give it a try. Good luck, and if you need any help or if you have any questions, do not hesitate to ask. And as always, keep on coding. I'll see you in the next lecture. Welcome back. Today we're going to be looking at a favorite design pattern of mine, which is the strategy pattern. As usual, let's have a look at a scenario. Let's assume that you have a web bot, which is like a web crawler, and you wanted to scrape some data from the internet. You might be interested in data content such as XML files, SQL files, comma-separated value files, perhaps JSON files, or some other type of data. Here is what it would look like. You have a website, you have a scraper, and the scraper then is going to scrape the XML data, it's going to scrape the SQL data, perhaps comma-separated values data, and maybe something else. Here's a simple pseudocode for our scraper. If the scraper encounters a document whose protocol is XML, then you can just extract the XML data. If the protocol is SQL, you extract the SQL data. And of course, if the protocol is CSV, then you extract the CSV data. This will create code bloat. This is not a good idea. Okay, so how do we deal with this? What is the problem with allowing the scraper to handle all the logic of scraping? There are a few reasons why you do not want to have the scraper handle all those different protocols. The scraper class will grow uncontrollably with each new data protocol. The extraction code that you put inside the scraper is not reusable. It's only in the scraper. And most importantly, the design violates the S.O.L.I.D principles, specifically the open-close principle, which states that we should extend the class, not modify it. One aspect of the solution would be to abstract each protocol, so the CSV and the XML, etc., into its own class, and then have the scraper call that specific class when needed. Now that is a good start. So let's have a look at it. So here is our original scraper architecture, which was pretty bad. Let's have a look at the slightly modified architecture right now. So we start the same way. We have a website, then we have a scraper, but now the scraper delegates to a handler that understands a specific protocol. So we'll have a handler for XML, we'll have a handler for SQL, and we'll have a handler for comma-separated values. So this is a much nicer way of doing this. We defer the decision about which algorithm to use until runtime. Obviously, the scraper will only know which algorithm to use when it encounters the specific data, when it's scraping the website, and that can only happen at runtime. Next, we expose the clients, which in this case is the scraper, only to the interface of the algorithm and never to the specific implementation. In other words, all the handlers will expose exactly the same interface. They will just do different things in terms of the protocol that they will use to extract the data. And why do we do that? Well, because this will allow for seamless substitution. At any given point, if we want to change the handler, we simply add a new implementation of the interface. The scraper at the time wouldn't be affected. And also, we use composition to loosely couple the handler with the parent decision-making class. In other words, we embed the handler inside the scraper. So we basically use composition for that. So what we have really done in the previous slide is we have defined the tenets of the strategy pattern. So let's have a look at the UML. So you can see that we have a strategy interface. It has one method called execute, which accepts some data. And then we have specific implementations, such as concrete strategy A, concrete strategy B, concrete strategy C. These are the handlers. Notice also that we have a context. Context will be like our scraper. And notice that the context has an aggregation of one strategy interface reference. There's a composition here. Notice also that in the context, we have a set strategy method. That way, we can tell the context which strategy to use. So you can see the client there. You can see that the client uses the context, but also the client will tell the context which strategy to use. So for example, you see in the comment there that we have str is equal to new concrete strategy A, so that's created, and then we simply set that strategy to the context, and then we tell the context to process that. And then if we want to use a different strategy, then we can supply a different strategy and use the setter to set that as well. So this, in an essence, is what the strategy pattern is all about. The main idea of the strategy design pattern is to extract related algorithms or any piece of code, such as concrete strategy A, B, and C, into separate classes and define a common interface for them. In other words, this is a very dynamic design pattern that allows your code to be flexible and depending on the runtime dynamic. That's very important. The strategy pattern, I would say, is the crowning jewel of all the gang of 4 design patterns. Next, we're going to look at the architecture of the strategy pattern. See you then. Welcome back. The strategy is considered to be one of the most practical design patterns. You will find yourself using it again and again. Here is its motivation as coming from the gang of 4. Define a family of algorithms, encapsulate each one, and make them interchangeable. Strategy lets the algorithm vary independently from clients that use it. How is the strategy pattern utilized with other gang of 4 patterns? Well, state design pattern can be considered as an extension of strategy. Both patterns utilize composition at their core, which means that they allow the modification of their process by delegating work to helper objects. Strategy makes these objects completely independent and unaware of each other. However, the state design pattern allows the objects to alter their behavior when the internal state changes. We will cover the state design pattern in this course. Command and strategy seem similar, but they have slightly different motivations. Command pattern allows for conversion of any operation into an object. Strategy allows for objects to achieve the same thing, but in different ways. When do you use it? You use this pattern to abstract the business logic of class from its implementation details so that it can be plugged in. You should use it when your class has a potential conditional statement that switches between different variants of the same algorithm. Use the strategy pattern when you want to use different variants or version of an algorithm within an object and need to have the ability to switch from one algorithm to another during runtime. When not to use. If you only have a few algorithms and they rarely change, it might be unnecessary to overcomplicate your code with new classes and interfaces. You'll just have to make a judgment call. What are the pros? In the strategy pattern, the behavior of a class should not be inherited, but instead the behavior should be abstracted and encapsulated using interfaces. This is compatible with the open-close principle, which proposes that classes should be open for extension, but closed for modification. You can introduce new strategies into the context without breaking any client code. This follows the open-close principle. What are the cons? Clients must be aware of the differences between strategies to be able to select a proper one for the task at hand. Also, in Dart, you can use anonymous functions just like you could a strategy, but it will not be as clean a code. We'll see an example of that in our coding. So what are the design considerations? First, you identify the algorithm that can vary depending on the circumstances of the context. Then, you declare the client interface, which will be the strategy contract for all the variants of the processing algorithm. Next, you implement each interface for the specific algorithms you have identified. Then, you add a private field to the context class to store a reference to the strategy object. Also, provide a way to initialize the specific strategy in the context. We usually do that through a setter. Note, if this strategy needs access to some context data, then provide a way for the strategy to access such data. Finally, clients of the context must be able to properly initialize the context with the correct strategy for a given circumstance. Let's have a look at an example of a strategy pattern. So we have seen this before. We have a scraper and then we have a couple handlers. We start with an interface, which is our data extractor. And we basically say extract some data from a source and return the data itself. We also have a scraper, which is our context. And notice that the scraper aggregates the strategy. And notice also that we have a way of setting the strategy through a setter. And then all that we have to do is just create new versions of the extractors. That is all there is to it. It's a beautiful design pattern, very simple, very powerful. All right, so next we're going to see the strategy pattern in action. We're going to code some of it in Python. See you then. Welcome back. Let's have a look at some code for the strategy design pattern within the context of Flutter and Dart. What you see here on the screen, we have a simple choose your renderer dialog with 3 radio buttons. When I click on render image, it renders an image. If I click on render button, it replaces that and renders a button. And if I click on render widget, it renders some kind of a widget. So this is a pretty straightforward workflow. The question is, how did we implement this? Let me just put it back into render image. So let's have a look at the UML diagram. We have an abstract renderer class, which has one method, render, which returns a widget. And then what we do is we extend that with 3 separate classes. We have an image renderer, we have a button renderer, and we have a widget renderer. So what you see here, these 4 classes, that basically comprises of a strategy design pattern. Now, if you look at the main page state, which is the one right here in code, main page state, if you look at that, what you see is that we have a renderer aggregated inside the main page state. And whenever you click on any one of the radio buttons, what that does is it grabs the corresponding strategy and uses it to do whatever the strategy does. And in this case, what it does is it simply renders or displays that particular widget. The nice thing about it is that when you look at the underscore main page state class, it is not aware of what the renderer is going to do. It simply renders it by calling the abstract render method. And this is where the simplicity and the power of the strategy design pattern shines. So let's quickly have a look at it. So here we have our main page state. So basically, if you go into main.dart, you can see that it's a very, very straightforward, simple application. In the build, we have our title, we have the theme, and we have the home. Now the home is our main page. If I go now into the main page, you can see that all that the main page does is it keeps track of the renderer, just as we've seen in the UML diagram. And before we look at how this main page state class uses it, let's have a look at the renderer. So the renderer is pretty straightforward. We have an abstract class renderer. It has a method render, which returns a widget. And then we have 3 subclasses. We have the image renderer, which simply just returns an image asset. By the way, this asset is right here. You can see on the left-hand side inside our images. Next, we have a button renderer, which basically has an elevated button code in it. And then finally, we have a widget renderer, which basically has a gesture detector widget. Inside of it, we have a row widget, which inside of it has a few children. The children are an icon, a text, and an icon, which is exactly what you see when I click on render widget here. This is the class that gets called, and it simply renders an icon, a text, and an icon. Notice also that the nice thing about this widget renderer is that it actually comes with a gesture detector. So if I show you here, let me just get rid of that. If I click on it right now, you can see that it actually tells you that I have tapped the row widget, and you can see that right here. This is pretty powerful. So let's go now into our main page. And you can see that in our main page, we keep track of the renderer itself. So whenever I click on any one of these buttons here, what that does is it assigns a different renderer based on the user action. So here is how we track the renderer. If you go into the list of the radio buttons, you can see that we have one that says render image, we have one that says render button, and we have one that says render widget. And notice that whenever you click on that, it simply assigns a different renderer. This is pretty cool because based on the action, you assign a different renderer. But here is the power, if you will, and the simplicity of the strategy design pattern. Because if we go now into this area right here, this container right here, you can see that all it does is it's a container for a child widget, and it gets the child widget by simply calling the render method of the current renderer. In other words, this class, the main page state, is not aware of which renderer it uses. And that's very powerful and a very important architectural strategy, if you will. Okay, so this is basically it. I hope that you really like this pattern. I absolutely love strategy pattern. It's my favorite pattern. Please note also that in one of the exercises that you are given for the strategy pattern, there's an extra class in here. See this one, shipping.dart, when you're going to refactor it so that it actually uses a strategy pattern as part of your exercise. The reason why we put this shipping.dart in here is so that you can maybe play around with the UI that we have already created so that you have a bit of a visualization, but that's completely up to you. All right, I hope you enjoyed this, and I'm going to see you in the next video. And as always, keep on coding. Welcome back. Let's have a look at a few exercises that you can do to understand and practice the strategy pattern a little better. So let's have a look at the exercises. Exercise number 1 is we've provided you with a source code, shipping.dart, which needs to be refactored to use the strategy pattern. Your task is to identify the main issue, correct it by refactoring the bad code into a number of strategies, write some sort of a main with simple UI to test your code. You will need to test the following. When the user switches the shipping method, you should be able to dynamically switch which algorithm is being used to calculate the shipping cost. Either use a drop-down, like a menu, or a few radio buttons for your UI. That's your choice. After that, add a new handler strategy for another shipping carrier, which is Amazon delivery, with the cost of delivery being $3.25. Here is the code that we would like you to look at. This is shipping.dart, and there is a simple address. There are shipping options, UPS, FedEx, and Purelator. We have an order, which is basically who is going to ship it, where, and where is this coming from. And we also have the shipping cost calculator service. Now, this is what you will need to refactor, the shipping cost calculator service. That's a really bad code. All right, so have a look at that. For exercise number 2, what we would like you to do is go back to the adapter pattern code, so basically the lecture before this, and look if the code can be refactored to use the strategy pattern to make it more abstracted and maintainable. In other words, I would like you to have a look with a critical eye at that code and see whether it can be improved specifically using the strategy pattern. The adapter itself is fine, so you're going to be looking at something else in there. The hint is look specifically at how the code handles displaying the contact records. All right. So that's basically everything. I hope that you're going to have fun with it, and good luck, and I'm going to see you in the next video. And as always, keep on coding. Welcome back. Today we're going to be talking about a very exciting design pattern, which is the observer pattern. The observer pattern is a very interesting, useful, and dynamic pattern. The main intent of the pattern is to create an event notification mechanism between objects. Think of the relationship between a publisher and a subscriber. A subscriber subscribes to a publisher of events. When an event happens, the publisher notifies all the subscribers in its list that an event has happened. Let's look at the subscription process. You have a publisher, and the publisher has some sort of a state, some sort of data that you are interested in. You have a number of subscribers, and these subscribers can subscribe themselves onto the publisher's list of subscribers. Any subscriber can add themselves to the subscribers list, or when they're not interested, they can remove themselves from the subscribers list. This is how the subscription would work. Each subscriber can say to the publisher, hey, I would like to be on the list of your notifications. Please add me or please remove me. How does the notification work? You have the publisher, The publisher has a state, which is basically data that you're interested in, and there is a list of subscribers. Whenever there is a change in the data that represents the publisher's state, the publisher sends notifications to each subscriber about the change in the state of the data. The observer pattern is a behavioral design pattern in which an object, usually referred to as the subject, which is the publisher in our examples, the subject maintains a list of its dependents, called observers, which were subscribers in our examples, and it notifies them automatically of any state changes. This pattern perfectly suits any process where data arrives from some input that is not available at a predefined moment, but instead it arrives at random. For example, HTTP requests, user input from peripherals like a mouse or a keyboard, distributed databases and blockchains, etc. It's an incredibly useful design pattern. The observer pattern is also a key part in the well-known and utilized Model View Controller (MVC) architectural pattern. Next, we're going to look at the architecture of the observer pattern. See you then. Welcome back. Here is the actual UML diagram. Let's look at this UML in a little bit more detail. Imagine that you have some sort of a subject, and this subject has a state, and some process can set the state, meaning can change it. And then, of course, we can pull or get the state from the subject. So we have this encapsulation of some data that we might be interested in. We don't know, though, when the state is going to change. So what we do is we create an observer interface, and this interface at least has one method, which is update. The idea behind the update method is that we would like the subject to tell us whenever its state data changes. How do we do that? Well, we modify the subject to keep track of all the observers that are interested in a notification. We create two methods, attach and detach, to be able to add and remove observers. And we, of course, have the set state and get state from before. So this is clearly a composition. The subject has an aggregation of 0 or more observers who would be interested in knowing when there is a change in its state. Whenever the state is changed, when somebody changes the state, what the subject does is it goes through all the observers and its observers list, and it simply calls the observers update method. Notice how we're using here the strategy pattern because the observer is just a pure interface. So now we will create an abstract observer, which all that it does is it keeps track of the subject that it is interested in. So you can see that the subject has the observers, but each observer also has access to the subject. When the subject's data changes, the subject goes through all the observers, notifies them, and then each observer already has access to the subject, so it simply goes and checks, oh wow, the data has changed, let me get the new data. That's the idea here. Notice though that in the abstract observer, the update method is still abstract, it has not been implemented. What remains is we create the different concrete observers. And it is in those observers that we can now do whatever we need to do in the update method. So when the subject calls each one of the observers by calling the update method, notice that the update method basically just states that we grab, for example, the observer state to be whatever it is that we want to extract from the subject's state object. The observer pattern is one of the most useful design patterns. Here is the motivation of the pattern as stated by Gang of 4. Define a one-to-many dependency between objects so that when one object changes state, all its dependents are notified and updated automatically. Some of the other similar design patterns coming from Gang of 4 would be chain of responsibility, command, and mediator. All of these, chain of responsibility, command, mediator, and observer, they all address different ways of connecting senders and receivers of requests. Chain of responsibility is used to pass a request sequentially along a chain of receivers until one of them handles it. In other words, chain of responsibility sends a notification, but it expects only one of the dependents to actually respond to it. Command is used to establish a unidirectional responsibility between a sender and a receiver. In other words, we know exactly who we want to do some sort of a task, we send that object a command saying do it. Mediator, which is also known as a controller, removes direct connections between senders and receivers, forcing them to communicate indirectly via a mediator or a controller object. It basically makes a more complex, but also more loosely coupled version of the observer pattern. When do we use it? Use the observer pattern when changes to the state of one object need to be known by other objects, especially when the actual set of the other objects is either unknown initially or changes dynamically throughout the lifecycle of the application. Use it also when an object or a set of objects need to observe changes in other objects and need to be notified in real time about those changes. When not to use. Because the order of notifications is potentially random, be careful about your requirements if order of notifications is important. What are the pros? You can introduce new subscriber implementation without having to change the publisher's code. This is compatible with the open-close principle. It also supports the principle of loose coupling between objects that interact with each other. You can establish relationships between objects dynamically at runtime. And if you think about it, the observer pattern is the key to reactive behavior, meaning something happens and then your application reacts. What are the cons? The order in which observers' subscribers are notified is potentially random. Debugging notifications can be difficult given the random nature of those notifications. What are the design considerations? Look for elements in your business logic that need to be aware of state data changes. Break it down into two parts. The controller/receiver of the events, this will be your publisher. The components that need to be aware of those changes, these will be the subscribers. Once you have done that, declare the subscriber interface, which should at least have a single update or notify method. Then declare the publisher interface and define the contract for adding and removing subscribers. Then you create an abstract publisher implementation with a mechanism for subscriber management and notification. Then you identify the state data that will need to be observed and create a concrete publisher implementation for that state. Define a way for subscribers to get access to that state. And then create the specific implementation of subscribers that you need. In other words, the objects that will need to be notified when data in the publisher changes. We're going to look in more detail at this when we actually code an example of the observer pattern in Python, and that's what we're going to do in our next lecture. See you then. Welcome back. Now let's have a look at how we can use streams to deal with notifying the UI that the data has changed. Unfortunately, with setState, it will refresh everything, so it does a little bit extra work here. If you use, on the other hand, stream and stream controller and stream builder, that will allow the notification to happen at the level of an individual widget. So you have your data, you have your change notification, but now the refresh command is going to target one specific widget within the widget tree. So especially when you have a complex widget tree, that is such a better and more efficient way of doing it. So let's have a look at the stream. So we have a stream builder, and a stream builder is basically a widget that builds itself based on the latest snapshot of interaction with the data stream. This is based around a stream controller. What is a stream controller? A stream controller works with a stream and something known as a stream sink. We use the stream sink to add data value, and we use stream to read it. So let's think of it this way. A producer is somebody who creates data. The producer puts the data into the stream sink. That then goes into the stream controller. The stream controller then produces a stream, and a consumer can be listening on the stream to get the data. This is what a stream controller does with a sink and a stream. You can think of it this way. Producer pushes events with data, and the consumer consumes those events with data. So basically what you have here is an observer pattern. Producer alerts the consumer that something has changed. Consumer is the subscriber here. There are a number of ways that you can use streams. Here is one. If you use the stream builder, that specifically works with a widget. And what the consumer gets, it gets an async snapshot with the data of the event. You will see that in code in a little bit. There's another way, though, in which the consumer can consume the data from the producer. You can use a listener. A listener works with a stream subscription. And the difference here is that a stream subscription is not a widget. So what you're seeing here is that on the producer side, the producer doesn't really care who the consumer is. It simply just pushes data into the sink. The stream controller then moves that data and makes that data available through the stream to the consumer. So what the consumer does is it subscribes to the stream controller's stream, and it can then consume or basically get those notifications. And we have two different ways. We can use a stream builder, which automatically works with widgets, or we can use a listener, which simply just works with data. It might sound a little bit confusing. It's a lot of information, but we will have a look a little bit later at the code. Now, one very important thing is that we cannot subscribe to the stream subscription with multiple listeners. In other words, if you go back here, you can see that when the producer talks to the consumer, there can only be one consumer. But in the observer pattern, we saw that we could have many observers. So let's go back here. So what this really is like a one-to-one observer pattern. But what we want is a 1-to-n observer pattern. So if you want to use this mechanism where many listeners, many subscribers wait for the data updates, we would have to use the following mechanism. Instead of this code, where you basically create a stream controller and it's initialized through a normal constructor, you can do this. The moment you instantiate your stream controller through a broadcast method, you will actually get a stream controller that will allow multiple listeners to get the notifications. All right, what we have here is a very simple demo of the way the stream works. We have 3 widgets in our application UI. We have an increment button, we have a decrement button, and we have counter text, which shows us basically the current state of our counter. We start with a 0. Now, the way this works is that if I press on this right now to increment it, you can see that we get a 1 here. And if I click again, it will just keep on adding. If I click here and then again, it decrements. That seems pretty straightforward. That's pretty easy to do. Well, the difference though is we do not use set state here. We actually use a stream controller. So let's have a look at that. So what we have here is we have created a counter controller. The counter controller is a class that contains a counter. A counter is just the value that you see right here. We then create 2 streams. We create a counter controller stream and we create an event controller stream. One stream will tell the controller that a button has been pressed, and the other stream is going to tell the widget that it should refresh itself. If you look up here, you can see that we have 2 events. We have an increment event and a decrement event. Notice that the stream controller works with an int because it will actually work with the counter itself. On the other hand, this other stream controller here, the event controller, doesn't work with ints. It works with our enumeration, in other words, with events. What we really have here is a communication that kind of hops from one part of data to another. In other words, if I press on the button here, if I click increment, this button is going to send a notification to the counter controller through the event controller stream. Whenever I press on any one of these buttons, what happens? Well, notice that we have a stream subscription listener here. And when we create the counter controller, which is the actual full controller class, notice that right away what we do is we set up a listener on the event stream. In other words, the counter controller itself becomes a listener for the event of any one of those 2 buttons being pressed. What happens in here is that the listener listens for an event. When the event happens, on the increment, it increments the counter, and on the decrement, decrements the counter. That's pretty straightforward. So in other words, whenever I click any one of those 2 buttons, this counter controller gets a notification saying, hey, there's an event, either increment or decrement, and I want you to know about it. So the listener will be notified. But then look at what happens inside the listener. Notice that the controller takes the other stream, which is the counter controller stream, goes into the sink, and it adds the current value of the counter to that sink. In other words, it sends a notification to whoever is listening to the counter stream that there is an event. Okay, so how does this work? Our UI creates the counter controller, which automatically starts listening for the events. So now let's go to those two buttons. So if we go into those two floating buttons, notice that on pressed, it goes into the counter controller's event sync and it adds the event. The moment it does that, look what happens in the counter controller. The listener will then, because it's listening on the stream, it's the consumer, it's going to get that event and it's going to say, oh wow, if the event was an increment, for example, you can see here, if you press the plus button here, you can see that the event being added is increment. And if you press on the minus button here, you will see that it's going to be a decrement. So what happens inside here is that the event stream listener gets the event and then it automatically updates the counter. Once it's done updating the counter, what it does is it then adds the current value of the counter to another stream. Now that stream is what takes care of the actual text. So let's have a look here. So what happens here is look at this child right here. In the child, we have a stream builder. The stream builder is the widget that is able to listen for stream events. So what we do is we initialize the stream builder with a stream. And the stream is simply going to be the counter stream, which is this one right here. This is the counter stream right here. So this is initialized with the counter stream and it puts initial data as 0 because initially it still needs to show something. So before it gets any data from the stream, it will initialize the widget with a 0. Let's look at what the builder is. So the builder takes, of course, the build context, but the more important thing for us here is the async snapshot int, the snapshot. That is actually the listener that will be listening constantly to check whether there's an event. And what this code does is basically it says, if the snapshot has data, then all that we do here is we basically go to the counter controller and we get the counter. Or we could have easily just taken, instead of the counter, we could have simply just put snapshot data. If I run this right now, you can see that it works perfectly. Okay, let's go one more time over Flutter streams to make sure that this process is clear to you. So let's recap. If I'm going to press the plus button right now, what's going to happen is this button right here is going to call the counter controller's event sync and it will add to it an event. So if I click on it right now, we should see in the debug console some information as to what is happening. So I'm going to press it right now. So notice what happened. My home page state just sent an event trigger, this one right here. And this is what it tells us is happening. Then this line gets executed, which is the event sync. So then what happens is inside the counter controller receives the event notification. So let's have a look here. And if you see right here, this is it. It just received the event notification. Then what happens is once the controller has processed the data, in this case, it just adds 1 or subtracts 1, it then is going to tell this widget right here that there's new data, that it should refresh itself. So what this does is it puts the data into that stream and we output this. You can see it right here, send event trigger. And then what happens is this will actually send an event to this widget right here. If we go back up here into the stream builder, you can see that this is what is printed here. In other words, it's a much cleaner, it's a little more complex, but it's a much cleaner way of controlling state management at the level of individual widget pieces within the widget tree. All right, so this is it for the code. Please go through it. It's very well documented. Have a look at the code itself. I've documented everything here. And experiment with it a little bit and try to understand what is happening and how it relates to the observer pattern. Now, as we've seen in the lecture, right now there's only one sync. If I press here, I can't send it to multiple widgets. So what I'm going to do right now is I'm just going to modify the code a little bit. I'm going to go into main and I'm going to put another widget right above this. I'm just going to basically just grab this whole copy that, and I'm going to add it right now behind this one. And if I run it right now, look what happens. We got some sort of an error. Like we have the 0, but nothing else is showing. So I'm just going to take you to the very top, and we're going to look at this error. And you can see that it says bad state, stream already has been listened to. The problem here is I have 2 listeners, but right now we have only set it up for 1 listener. So how do we fix this? The way you fix that is pretty straightforward. When you create the stream like this can only work with 1-to-1 subscriber to publisher. Just 1 publisher, 1 subscriber. If we want to be able to send the same notification to multiple subscribers, which is like the classic example of the observer pattern, all we need to do here is we need to use a broadcast factory. So it will create controller for broadcasting. So I'm just going to go broadcast. I'm going to remove that. Perfect. Let's run it right now. And as you can see right now, we have 2 widgets. And if I click just once, you notice that they're both changing at the same time. And that is because each one of them right now is receiving exactly the same data. I could be publishing to a number of different widgets. So this is now a more of a classic example of the observer pattern. All right, so this is it for this particular lecture. I know it's been a little bit different. We haven't really built our own observer in this particular code, but I would like you to go back to all of this code and think in terms of the observer pattern, in terms of what you see is happening in Flutter. Now, I will give you an opportunity to exercise the creation of the observer pattern. All right, in the next lecture, we're going to look at a very important design pattern, which is the state design pattern. All right, I'll see you then. And as always, keep on coding. Welcome back. Let's have a look at some exercises for you to do for the observer pattern. Exercise number 1. I would like you to create a UML diagram for the part 2 code that we looked at in the coding section for the observer pattern. Specifically, that was the one where we had the increment button and the decrement button, and then we had a text widget that was showing the current value. Look at how the streams are utilized in passing state data between the buttons and the text widget, and create a UML sequence diagram that shows that interaction. Include the following objects in your sequence diagram: the floating action button, the stream sync for the event, the stream subscription, the stream sync for the int, which is for the counter value, and the stream builder for the int, which is the widget that actually builds and shows the text that shows the increment or decrement value, and also the text itself. Now, you don't have to use any specific tool. All you need to do is, just for practice, try to do it even by hand on a piece of paper. I'll provide you with a solution so you will be able to compare. Exercise number 2 is a little more ambitious. Using the grid code from part 1 code that we looked at in the coding section for the observer pattern, create the following modifications. Using a timer, refresh each tile of the grid at every second. Add a number inside each tile that is randomly generated at every tick. Make sure that each tile in the grid becomes an individual subscriber to the timer tick event. When the time ticks, notify each tile widget that a new timer event has happened. When that happens, simply generate a random number between 1 and 10 and place it in the middle of that tile. Use what you have learned about Flutter streams to refresh each tile widget with the new data. This is more ambitious because it's going to be a little bit more difficult, as you are going to have to deal with literally 64 subscribers. I suggest that you maybe start the grid with just like 8, but that's up to you. But the idea basically is that I would like you to have the grid refresh each tile as a separate stream, so that when the timer, and this is just the timer that we're using is just the Flutter timer, the timer is going to be the publisher and the subscriber are going to be all the tiles. Good luck with it. I hope you're going to find this challenging. It definitely is. And this is about halfway to creating the game of life simulation. So give it a try. Ask any questions that you would like to in the forums and I'll help you. And otherwise, I'll see you in the next lecture. And as always, keep on coding. Welcome back. Today we're going to talk about a very exciting and interesting design pattern, the state design pattern. Before we look at the details of the state pattern, let's talk a bit about what states, actions, and transitions are in context of a logical workflow. Consider a simple scenario of the workflow of making toast in the morning. We start with the toaster being idle, basically it's doing nothing. We then insert a slice of bread. We then pull the lever to start toasting. We pull it down. The bread is then toasting. At any point, we can eject the bread. Once the bread has been toasted, it is automatically ejected by the toaster. We can then remove the ejected bread, which brings the toaster to an idle state. I know that it's a little strange to kind of like break down such a simple process into these steps, but what we have done here is we have created a very simple algorithm. How do you translate an algorithm like that into code, and what does this have to do with the state pattern? Let's look at the algorithm and how we can break it down. Here is a little table where we have state, action, and transition. So the states are the states of the toaster. We can have the toaster being in an idle state. It could be in a state where the bread has been loaded. It can be in a state where it's toasting the bread, and it can be also in a state where the bread is ejected. Notice though that bread ejected and bread loaded are very similar states. Let's have a look at the action. For example, when you are in an idle state, what you can do is you can load the bread. If you're in the bread loaded state, you can start toasting, or you can just take the bread back. If the state is in the toasting, the toaster is actively toasting the bread. You could either eject the bread, that happens many times. You see, oh, wait a minute, I'm hoping that it's not burned. So you just stop the toasting process. When the toaster is done toasting, the action could be that it simply has finished toasting. And a similar thing for bread ejected. Transition is basically where you move from one state to another. So for example, if the state is idle, and the action is load bread, we then move into a new state, which is the toaster has the bread loaded. If we are, for example, in the bread loaded state and the action is remove the bread, we transition into the idle state. Or if we're in the bread loaded state and we pull the lever down, which is the start toasting action, then the transition is such that the toaster goes into the toasting state. I know that this can sound a little bit complicated, but the important thing is to just remember the following three things. A state defines one of the states in which a particular device or action can be. Action is something that we can do to change the state, or we can affect the state. Transition is how the action has changed the state. Let's represent this workflow as a finite state machine using a simple state diagram. So here is our table, and we're going to translate this table into a state diagram. So the first thing we're going to do is we're going to put the 4 states into our state diagram. So we have the idle, bread loaded, bread ejected, and toasting states. Next, we're going to specify which one of those states is the first state. So that is our initialization. And then what we do is we have the actions. If I'm in the idle state, I can then insert bread, which transitions me to the bread loaded state. If I'm in the bread loaded state and I pull the lever down, then the bread gets pulled down and we move into the toasting state. When the toaster is done, then it goes into the bread ejected state. And then finally, if I remove the bread, then it goes back into the idle state. So this is like a full loop, but that's not the only thing that can happen. For example, if I'm in the idle state and I go to insert the bread and the bread is loaded, I don't necessarily have to pull the lever. I could simply at that point remove the bread. So you can see that we have all these other actions that show us the things that we can do when we're in a given state. What you see here is a very simple state machine, and this is a state diagram that shows us, first of all the different states, the actions that we can perform on those states, and also how we transition from one state to another based on the action. So what does all this have to do with our state pattern? The state pattern is a behavioral software design pattern that allows an object to alter its behavior when its internal state changes. As you have seen, state pattern is similar to the concept of finite state machines. In other words, there's a finite number of possible states with discrete transitions between those states. This pattern can also be interpreted to some extent as a strategy pattern, which is able to switch a strategy through invocations of methods defined in the pattern's interface. We'll see what that means in just a bit. Here's a bit of an abstract UML diagram for a state pattern. Let's have a look at this in more detail. We start with something which is the context. This is the actual thing that can change state. For example, in our toaster example, context would be the toaster. Next, what we do is we have a state interface. This interface will be used to define all the different states that we have in our state machine. Notice that context aggregates state. This is how you could do a transition. You could set the state in the context to be a specific state, and then you can initialize that state with the context itself. And then what you can do is you can invoke an action on that state by basically saying toast or eject or action A. Here what you see is an abstract state class, which gives us the ability to look back at what the context is. Notice that the state defines a few actions, like action A, action B, action C. These actions are the actions for our state machine. As you can see, our abstract state aggregates context. So what we have here is that context keeps track of a state, but our state can also have an aggregation of the context. But let's say we have a concrete state, like concrete state 001. The concrete state is going to have a number of actions, and the transition that you could do from one state to another, for example, inside concrete state 001, we could create a concrete state 002. We can then initialize it with a context, and then we can tell the context, please change your state to state 002. And here we have other implementations of the state. And how would the client use this? The client can do two things. First of all, the client can create an initial state, for example, concrete state 001, and it can then create the context initialized with that state, and it can then do an action on the actual context. Here's a sequence diagram that shows a client that is requesting for the context to do some sort of an action A. Context then delegates action A to whatever state it is in at that time. Let's say that the state happens to be concrete state 001. So what context will do is it will ask the state to execute action A. What the concrete state 001 will do based on action A, it will decide at that point what should happen, what kind of transition should happen when action A is called on that particular state. And in our case, you can see that we have a simple delegation where it says move to next state. And what it does, it creates concrete state 002, initializes that with the context, and then it sets the state of the context to be the concrete state 002. So the context has transitioned from concrete state 001 to concrete state 002. So when the client calls the context with another action, like action B, inside the context, the actual action B is going to be executed on the current state, which happens to be concrete state 002, which will possibly do the same thing. It will also move it to the next state. What you need to get from this UML diagram is that the states are aware of the transitions. They're aware of what should happen for a given action on a given state. So the way that these actions move from one state to another is that the states themselves know how to do it. This is an important distinction. All right, we'll learn more about state design pattern in the next lecture. We'll look at a classic example of a very simple state machine and its UML design. Welcome back. Let's continue with the state design pattern. The state pattern is absolutely an awesome design pattern. Here's the motivation of the pattern as stated by a gang of four. Allow an object to alter its behavior when its internal state changes. The object will appear to change its class. What are some of the design patterns that are either similar or dependent on the state pattern? State, strategy, bridge, and to some extent the adapter pattern have very similar structures since they are all based on composition. This allows them to wrap around other objects and delegate work to them. State pattern, to a great extent, is an extension of the strategy pattern. Both patterns allow the context to change its behavior by delegating work to composited helper objects. The strategy makes all the objects independent and unaware of each other. But state pattern allows for the change to its behavior when its internal state changes. Please note also that state objects are often singletons. When do we use the state pattern? You should use the state pattern when you have an object that changes its behavior depending on its internal state, especially when the number of possible states is non-trivial. So look for many if-else statements that change behavior of the object. You also use it when you have a number of rules that act on an object based on the object's state, especially when modeling real-world workflows. When not to use. If the state transitions are very simple and infrequent, it might not be advantageous to use the state pattern as it would add unnecessary complexity. What are the pros of using the state pattern? State pattern reduces conditional complexity by removing bulky and hard to maintain if-then-else or switch case statement logic. You're able to introduce new states without changing the existing state classes or the context. This follows the open-close principle. All the code related to a specific state is in its own separate class. This follows the single responsibility principle. What are the cons? The state pattern can require a lot of code to be written, which grows in complexity as more states are modeled. Here are some of the design considerations. So what you do is you look for a class or logic, if it's distributed across a few classes, that has some rule-dependent or state-dependent code. This will be our context. Declare the state interface and design state-specific method behavior. For each actual state, create a concrete state implementation. In the context class, add a reference to the state interface with a public setter. For each state conditional, implement the corresponding method in the context class. Switching the context state will be done by setting the correct state instance. Now note that this can be done within the context itself, in the state instances, or even by the client. Let's look at another quick scenario and how we would model it. The scenario is a classic, a simple on-off light switch. We have two states. We have the light being on and the light being off. And we have one very simple action. You simply flip the switch. If the light is off and you flip the switch, it will be on. If the light is on and you flip the switch, it's going to be off. Very simple. So we have two states, light off and light on. We start with the light off, and we have very simple transition, which is just switch and switch. This is a very, very simple state machine. So as you can see that when the light is off and I click the switch, it goes into light on. If the light is on and I flick the switch, it goes into light off. So let's see now how we would model that using the state pattern. Our context would simply be the light. The light has a state. We have two methods for manipulating the state. We can get the current state of the light. So let's say if we wanted to find out is the light on or not. And we also have the ability to set the state. And we have a business method, which is switch. This is our state. We'll just have a simple do action, which accepts context. And we'll also have a simple name method that would just tell us what the particular state is. As stated in the design considerations, our context, which is light, will aggregate the state. We have two states. We have light on and we have light off. Pretty straightforward. The client will start the light with light off, and then the way you would use the light is you simply take that light and you just hit the switch, and you can do it repeatedly. Light on in its do action will do something very simple. It will take the context and it will set the state of the context to light off. And for light off, we do the opposite. The important thing to get here is that each one of the states is aware of the other state. Light on knows that it should set the state to be light off, and light off knows that it should set the state to be light on. All right. So this is everything for this particular lecture. What we're going to do next is we're going to code an example of the state pattern in Python. We'll see you there. Welcome back. Let's have a look at how we would code a simple practical example of the state design pattern. So let's talk about coding traffic lights. Let's code the behavior of traffic lights using the state design pattern. This pattern is a good candidate to model such behavior because we would like to have the ability to simply tell the traffic lights to just go to the next state while the actual state transition is hidden behind context. So the idea is pretty simple. We have a traffic light. We start with a green, then we go into a yellow, then we go into a red, and then from red we go back to green, and this repeats. So basically, we're looking at something like this. Pretty straightforward. We all have seen traffic lights before. So let's see how we would actually design and then code such a simple transition. Let's look at the steps that we need to consider. First, we will need to declare the state interface and design the state-specific method behavior. How will the state have its transition move from one state to another? For each actual state, we will create a concrete state implementation. So in our case, we will have a state for each color of the traffic light. So we'll have a state for green, for yellow, and for red. Now, in the context class, we're going to add a reference to the state interface with a public setter. The idea being that our traffic lights should let us know what state they are in actually. For each state conditional, we implement the corresponding method in the context class. So the idea basically is that the transition from one state to another is going to be coded within the states themselves. Now, switching the context state will be done by setting the correct state instance. And finally, this can be done within the context itself, or in the state instances, or by the client. So what I'm going to do right now is I'm going to go into the UML diagram, but it would be a good idea for you to just pause the video and think about how would you create, using the state design pattern, a traffic light simulation. Okay, so I'll show it to you in the next slide, but for you it would be a good idea to pause this video right now and just try to design it yourself. All right, so let's have a look. So we will have a traffic light state, which is going to be our state abstraction. It's going to have two methods, a getColor and the next, which is going to be the transition itself. And we're going to have three specific concrete instances. We'll have a green state, a yellow state, and a red state, and they will implement those two methods, the getColor and the next. Now, the actual implementation is going to be relatively straightforward. You're in the next method, you're going to accept a traffic light. We'll see what that is in a second. And we're going to simply change that to the next state, which is going to be from green, we're going to go into yellow. From yellow, we're going to go into red. And from red, we're going to go back into green. This is our context. This is our traffic light. Notice that the traffic light has a current state, which aggregates the actual traffic light state, which we initialize to start with a green light, which is the green state. Notice that we have a next method and we have a getColor. The next method will simply move the transitions behind the scenes, as you can see, being implemented in the green, yellow, and the red states. And of course, the color itself is just going to return the color of the state. And as you can see, the traffic light itself aggregates the traffic light state. So the traffic light state uses the context and the context aggregates the state. So next, what we're going to do is we're going to look at the actual implementation of this, the actual code. You can pause the video again, look at this diagram and kind of think about how you would implement this. Of course, the code itself has been attached with the lecture. So now what we're going to do is we're going to go into the code itself. Again, if you want to pause the video right now, do so. Otherwise, let's go in there. So let's go into the code itself. I'm going to run it first. I'm going to run it on Chrome. All right, here it is. So what you're seeing here is we have our green, yellow, and red cycle. And as you can see, this is periodically changing. We have a green, now we have a yellow, and now it's going to go into red, and then it will just keep on repeating. We also output which cycle we're in, basically which step in the transition. Okay, so let's have a look at the code itself. So as you can see here, we have the traffic light state, which is our abstract state class. We have the next method and the get color, which are abstract. Now let's have a look at the actual implementations. So we have three implementations. We have the green state, we have the yellow state, and the red state. Notice that the methods are relatively straightforward. What the green state does is it accepts the context, and inside the context, it sets the next state to be yellow state. And it returns the color of this, which is the green state, to be green. Yellow state does the same thing. It simply moves or transitions the state from yellow into red and returns, of course, the color itself is yellow. And then the red state moves the transition into the green state. So basically what we have is we go from green to yellow, from yellow to red, and from red to green. And here is our context class, our traffic light. Notice that the traffic light aggregates the current state. We initialize it first to the green state, and then the next method on the traffic light, all it does is it basically calls the current state and asks for it to transit to the next state. And then the color simply returns the color of the current state. Notice that when we call the current state next, it actually provides the context as input. Okay, so now let's have a look at the actual class itself. The class itself is pretty straightforward. What we have obviously is a timer. So first we have our traffic light right here, which is our light. We initialize the cycle to 0, so we're basically starting with a cycle 0. In our init state, what we're doing is we're starting a timer. The timer is just a simple periodic timer that basically creates a notification every 3 seconds. The actual notification, what it does is it calls the set state on the widget, which basically refreshes the whole widget tree. And what it does is it adds 1 to our cycle and calls the next method of our traffic light. And inside the build, actually, it's pretty straightforward. We create a nice little container, 150 by 300, so it's basically a rectangle. We use the box decoration, we create a border, and then the light inside the border is the current traffic light. And then we output the cycle. This is pretty much it. It's a very straightforward usage of the design pattern. The beauty of this is that if you look here, all that the timer has to do is simply keep on calling the next method, and the actual transition, the actual state changes are hidden behind the context. So this is what makes the state design pattern so powerful. All right, so please have a look at this code, look at the UML diagram, and otherwise I'm going to see you in the next lecture. And as always, keep on coding. Welcome to the course assignment. We're going to design, architect, and develop a version of John Conway's famous Game of Life simulation. Why this particular project? There are a few reasons. First of all, we think it will be fun. It's going to utilize all the design patterns we have learned in this course. It is complex enough that a good architecture will make a huge difference, but it is simple enough that you can develop it within the busy schedules of your lives. And also, it will involve some interesting and dynamic UI design. What is a game of life? The game of life is a cellular automaton invented by the British mathematician John Conway in 1970. It is a zero-player game. Its evolution is determined by its initial state, requiring no further input. You interact with the game of life by creating an initial configuration and then observing how it evolves. This is why it's a zero-player game. You start with an initial state, then at a certain time interval, which is what we call a tick here, you go into the next state. So you basically take the data from the initial state, and then at the tick of time, you go to the next state. And then when the time ticks again, you take the current state and you go into the next state. So basically your current state becomes the next state, and this goes to infinity. The idea is that the game of life is an evolving game. You set a certain initial state, and then the game just progresses. You don't even know exactly how it's going to turn out because it depends on what kind of input you gave it. The universe of the game of life is an infinite two-dimensional orthogonal grid of square cells, each of which is in one of two possible states. It's alive or dead. Or basically you can think of it as populated or unpopulated. Orthogonal in this case simply means a grid where the lines that intersect are at 90-degree angle. So for example, this is a very simple orthogonal grid, which is simply a 4x4. It's not infinite. We can specify that a cell is dead, unoccupied, with the lighter color, and we can show that the cell is alive with the dark color. So for example, this shows that you have one organism alive in row 2, column 3. Let's define what neighbors are. When you look at this picture, you can see that we have one alive cell in the middle of this grid. The neighbors are all the cells around it that touch it. If your alive cell happens to be on the edge of the grid, then of course it will have less than 8 neighbors. It's going to have 5 neighbors. And if you happen to be on a corner, then you will only have 3 neighbors. Every cell interacts with its 8 neighbors, which are the cells that are horizontally, vertically, and diagonally adjacent. At each step in time, the following transitions will occur. This is where you have the workflow of the game. Any cell with 2 or 3 live neighbors survives. Any dead cell with exactly 3 live neighbors becomes a live cell, so it's like a birth. And all other live cells die in the next generation. Similarly, all other dead cells stay dead. Let's have a look at this in a little bit more detail. These are the 3 main paradigms of the game. 1, any live cell with 2 or 3 live neighbors survives. So let's look at that one first. In these examples right now, we will be looking always at the middle cell as the cell we're talking about. So this one has 2 live neighbors. We're just showing the slightly darker color as being live so that you can discern which cell we're talking about versus which are the neighbors. So for example, this one has 2 live neighbors. This one, for example, has 3 live neighbors. And this one also has 3 live neighbors. Any one of these 3 configurations means that the middle cell survives. You do this logic for every cell in your grid at the same time. Okay, all of these are computed at the same time. So we're just looking at one cell right now, but this same logic would be happening with all the cells at the same time before you transit to the next state. Okay, let's look at number 2. Any dead cell with 3 live neighbors becomes a live cell. So basically that becomes a birth. So for example, here in the middle, we see that we have a dead cell. There's nothing there. Here we also have a dead cell in the middle. And here we also have a dead cell in the middle. But notice that in each case, that middle cell has exactly 3 live neighbors, which means that the cell is born. Now let's look at number 3. All other live cells die in the next generation. Similarly, all other dead cells stay dead. So for example, here we have a scenario where the cell has 4 neighbors. Here we have a scenario where it only has 1 neighbor. And here we have a scenario when it has no neighbors. So in the first scenario here, you could basically look at it as the cell is going to die because of overpopulation. In the second and third diagrams, the cell will die because it is lonely. Here is another example of overpopulation. This will result in the middle cell being dead. Now, in all these examples, you could ask, why is it that we don't show the other cells like in the outcome? Because we're just showing you a single cell computation. You would then apply the same logic to every other cell in the grid. Now, it doesn't have to actually happen at the same time, but it has to happen within the same transition. Here is an actual demo from YouTube of what the game of life could look like when you just let it run. And as you can see, some very interesting patterns emerge just because of these simple rule interactions. So depending on what your initial state is, you might have a lot of different things happening here. This is pretty exciting and pretty interesting. Sometimes what will happen, as you see, for example, at the top, we have behavior known as oscillators. You can see that it's basically moving back and forth. It's the same pattern that is moving back and forth. So this is very, very interesting. So your task will be basically to design, which is write down the requirements and constraints on the application, design the user interaction with the game, what input and output will be needed, create a high-level diagram for all the main pieces, which is the objects that you will need and how they will interact. Then you will architect. Expand your design into specific classes and objects and look what design patterns could be used in this application. Hint, you could use all of them. Make sure to abstract the UI layer so that it can be easily swapped in and out. Create any necessary UML diagrams to make it easier to follow your own design. Once you have all that, you will develop, which is write the code for the application based on your architecture. Make sure to document your code well, and then test it. Here are some considerations, or some hints if you will. If you are unsure about some of the Python APIs you will need, then develop a simple POC, which is a proof of concept first. This allows you to explore and test the APIs before you architect the solution. If your architecture is well hashed out, then you should be able to create a quick POC with minimal UI, initially at least. You could, for example, output the transitions into just debug console. You don't have to necessarily start drawing anything on the screen, just so that you know that at every tick you're computing things properly. And you can also start with a small grid, maybe like a 10 by 10 or a 16 by 16. Concentrate initially on object communication and process workflow. For example, generating the tick at regular intervals. Use a timer or create your own timer. Before you code anything, consider going through a few high-level iterations of your architecture to ensure that you have captured the following: all the data objects, all the data constraints for validation, and also the process algorithm for the transitions. How do you actually find the neighbors, and how do you make sure that a cell is dead or alive? We have to assume a certain finite grid. The grid, for example, could be your whole screen where each cell is a pixel, or 4 pixels, or 10 pixels. Make sure that the UI is flexible, so it would be easy to reskin, for example, stylize, the look and feel of the game. Separate the UI, like the classes of the UI, away from the rest of the code. Think about what design pattern you would use to create pluggable renderers for UI. Think perhaps strategy. This would be both the grid, which is the UI, as well as the stylization of each cell in the grid. You should be able to swap out, for example, how you present the animation. Consider also what UI elements for initial state should be. Are you going to initialize your grid by using like certain buttons like start, stop? Are you going to have sliders? Maybe you will use a slider to expand the grid or shrink the grid. Or perhaps you will have text box input, which will basically say, hey, I would like a grid which is 20 by 20. And then you have to consider how do you input the initial state, which is where the organisms are. This could be just simply tapping on the screen, for example. Here are some support materials for you to consider. Please have a look at the Game of Life Wikipedia page for more research. There's also sample YouTube visualization, and you can find a lot of visualizations on YouTube if you simply plug in Game of Life or John Conway's Game of Life. If you want to use some UL modeling tools, here is a couple that are free, at least in a basic form, but you could actually just do it by hand and take a picture of it. So if you, for example, want any feedback from me, you could very easily just draw it by hand, take a picture, and then post the picture in the forums. And that's good enough. You don't have to necessarily create a super duper looking UML diagram. I have provided you with some starter code, and I would like you to analyze the code that I have given to you. Break it down into organizational units such as, for example, the generation timer, the display, the next generation processing, etc. The code that I'm giving you does not actually have a timer. The generation is calculated whenever I click on the button. So what I would like you to do is make that into a timer. And as a hint, you could then use an observer pattern for what happens when the timer generates a tick. I would like you to come up with what design patterns could be utilized to make this code, first of all, architecturally flexible, written with interchangeable logic. So I could, for example, just replace the GUI for it relatively easily. Think, for example, of being able to pause the game as well. So think ahead of what could I do with the UI, for example, so that I could pause the game, or being able to persist and then load back the game. For example, let's say you've been running it for 20 hours and you would like to save it so that later on when you restart your system and when you restart your mobile device, it continues where it was. That's basically the main idea here. So let me show you now the actual code quickly. Here, I just have a very, very simple single class that basically creates a game of life. And it starts like this. And now if I click repeatedly, kind of pretending to be the timer, you can see that the generations are being calculated. So I have already given you all the logic in here. And what I would like you to do is, first of all, break it down into separate classes and then use specific design patterns as you see fit to recreate this code to be much more flexible and to be much more interchangeable. The code is provided as an attachment with the resources in the course. Okay, so this is basically it. Please have a look at this, and I'm going to see you in the next lecture. And as part of the assignment, at some point, I'm going to post an architectural document for you to kind of like check, whether you're on the right path or not. So look for a quick architectural exposition in some later lectures/documents. All right, see you soon, and as always, keep on coding. Welcome back. Let's have a look at how you would start an actual architecture for the game of life simulation. You can go through the following design steps. First, write down the general workflow of the application based on what you have read about it, based on the demos that you've seen, etc. Define the inputs and the outputs in general terms. Perhaps explore a validation as well. That's not really necessary, but you can start thinking about that as well. Next, you extrapolate and outline the main agents in the application. These are the objects that will do the work. For example, we could have a grid renderer or a tick daemon, which is the timer. At this point, you're looking for work-based relationships and not really methods or variables. Define how these objects will communicate. In other words, some objects are going to require for something to happen. Like, for example, compute the next generation. You might have an object that deals strictly with that. Start thinking about what design patterns you will want to use and build your first proof of concept. And then refine. Keep on going through this as if it was a development cycle. So let's look at one of the first steps for this. So here is a high-level workflow. Create and initialize the simulation grid. It could be n times m, for example, 20 by 80 or 100 by 100. Initialize the starting organisms, which are the occupied cells on the grid. That will be your initial state. Start the simulation with a tick interval of x seconds. It could be 1 second, it could be 3 seconds, it could be 0.1 seconds, depending on how quickly you want the refresh of your generations to be happening, how quickly you want your simulation to refresh. Next, at each tick, you're going to compute the new generation of organisms. One way that you could do this is you could loop over each element on the grid or on the board, and you compute if the organism at that location should live or die. Then you render the new generation once you have computed all of the cells in the grid. And then at some point, if the user wants the simulation stopped, then you stop it. So you should give your user the ability to stop the simulation. This is a very high-level workflow, but it's a good starting point. We can then begin to refine it and add more details such as input and output, as well as any validation needed. So the next thing that you would do here is you would start to think of what are the main objects that can do all this. Congratulations, you have finished the course. So where do you go from here? We have covered what are, in my opinion, the most fundamental set of design patterns in the software engineering universe. This is a good start. Actually, it is a great start. What is needed now is practice and more practice. The best thing to do is to try to utilize these patterns in your projects. Break your projects down across object lines and remember the S.O.L.I.D principles as a good guide to beautiful code. There are more patterns to learn, so I suggest that you explore those as well. We will be creating other design pattern courses in the future, so hopefully you're going to look into those as well. A few other topics to really sink your teeth into would involve the following when it comes to software architecture. You can look up architectural patterns, especially anything to do with peer-to-peer communication, anything involving microservices, and anything to do with event bus architectural approach. These are pretty powerful and important. Threat safety is another topic that is definitely worth exploring. And I would look into the producer-consumer problem as a great exploration to understanding threat safety issues. State management, which is especially important if you're interested in Python gaming. It's very important for you to understand how applications manage their state data. This is especially very clear in mobile applications where you're moving between different screens and you need to remember what was, for for example, created in a previous screen. Alright, that's it for this video. See you later. I would like to thank you for being a part of this course. I really hope that you have learned some useful things, and I hope that our paths will cross again, and I'll be able to teach you something useful in the future. Take care, and as always, keep on coding.